Right, we'll give it a minute. I think I can see people starting to come in. That's great. So, okay, well, welcome if you're just joining us. I'm Rob Massey. I'm Deputy Director of the Royal Astronomical Society, and I'll be hosting this event today. Right, we'll give it a minute. I think I can see people starting to come in. That's great. That double voice you can hear is because YouTube is not muted on my machine. Okay, well, welcome if you're just joining us. I'm Rob Massey. There we are. And that's just because we're watching for questions on there as well. So this is running on Zoom with people who've registered and signed up. You will be Zoom panelists or Zoom participants. We're the panelists, the people you can see. If you want to ask questions at any point, please use the Q&A box that you can see, and we will be able to see those, answer them. Perhaps panelists, if they're very simple, might type in written answers or supplement those as well. We will also try to keep track of questions on YouTube as well, although I will be switching between screens to do that, so it might not always be as effective as you think. However, to return to the substance of this is a web event, a live event for observations of the Jovian ionosphere, the layer in the atmosphere of Jupiter, and we will be with our experts here, Tom Stallard from the University of Northumberland and Henrik, Melin and Paolo Taranti from the University of Leicester. We'll be talking you through live observations from the infrared telescope facility on the island of Maunakea in Hawaii, because of course, although it's daytime, middle of the day in the UK here, Hawaii is on the other side of the world. So the great thing is that we've got access to live data from a telescope at night. That's the wonderful thing about time zones and living on a round planet. The other thing, though, the exciting thing is that last week on the back of a similar event, or coinciding with a similar event, this team had time on the not long ago launched James Webb Space Telescope. It's sort of a relatively new telescope. Hopefully, most of the people watching have heard of it. 6.5 meter mirror infrared telescope, seen as the successor, not the absolute exact kind of same telescope, but the successor to the Hubble Space Telescope, which of course is still going strong. 1.5 million kilometers away from the Earth and gathering information about the universe, the distant universe and the solar system and everything in between from that position. So we'll be talking through what it's telling us in these new, this new data on Jupiter that these guys here will be talking through. So I think I've mentioned who's on the call here. I guess, actually, I was also going to mention in context, by the way, apart from what you're going to see today, if you want to look at Jupiter for yourself, obviously not in infrared unless you've got access to some quite swish equipment. It's actually very well placed in the night sky at the moment. If you're up at about 10, 11 o'clock at night in the UK and you or the similar latitudes and you look over towards the eastern sky, you wonder what this very bright object is. That is Jupiter in a clear night. It's really well placed at the moment. It'll be even better in November when it reaches its closest point to the Earth this year. So do look out for that. But that's not what we're here to discuss at any length. What we're going to talk about is the professional observations by the astronomers we have on the call here. So what I would suggest I do is bring in Tom, first of all, to give us an overview of what's happening and what the team's been doing. So over to you.
Thank you very much. So yeah, it's been a hectic month for us. We've had a series of different observations on different telescopes, which is unusual in itself. It's rare that you get time on more than one telescope at a time. But those of you watching on Thursday will have seen the culmination of that, which was, although it was cloudy in Maunakea, it was still nice weather enough to do observations, and we had simultaneous measurements of Jupiter's atmosphere using the Keck telescope, which is a 10-meter telescope on Maunakea, the NASA IRTF, which is a 3-meter telescope that we've been using for the entire month to monitor what's happening at Jupiter, and the James Webb Space Telescope as well, which we were very briefly able to show some of the results of that at the end of the night, but very little, because James Webb takes the data, then downloads it to the servers after it's taken. We managed to show it within the stream, which is kind of crazy. It's very rare a space telescope will feed information back that quickly, so it was pretty surprising that we were able to even do that. But that's why we decided a second stream on Monday, today, would be good, because it would give us time to at least have a first look at that data. And that's hopefully what we're going to have a chance to show you. But also we can show you some of the observations we've taken over the last month with IRTF. That's a program that was devised by my PhD student, Katie Knowles, who is in Japan right now, working with James O'Donoghue, one of our colleagues. So I don't know if they will be around because it's nearly midnight in Japan. So that sequence of data interleaved with some Keck observations we did, and all of this is built around another observation by the satellite Juno, which is orbiting Jupiter. So Jupiter is being observed from all sorts of instruments and all sorts of distances by Juno, but Juno, most importantly, was doing a measurement of the ionosphere on Thursday by looking at the radio signal beam back to Earth and using that to measure how much that signal is attenuated by the ionosphere, and using that to get a measurement of the absolute density of the ionosphere. So we're going to be talking about the outer layer of Jupiter, the most thin and far afield. In fact, let me share something and I'll show you what I mean by that. I need access to screen sharing, Robert. So
Lucinda's, I think I'm not quite host yet. Lucinda's switching over to me. So Lucinda's our education outreach officer who set this up.
So basically,
permission to do that.
When we look at these amazing images, in fact, behind you is an amazing image of Jupiter, this famous image from James Webb, where we see a mess of clouds and all sorts of sort of different layers of the atmosphere.
Right, you should be able to share your screen now.
Thank you.
There we go.
Which you can see in detail again here. You see all sorts of different stuff on this. Cloud layers, belt layers. You see the great red spot, which is a white spot in this image because this is a false color image. All of these are different wavelengths in the infrared. The green you can see is a sort of hazy layer up near the top of the planet. And this is all the stratosphere, so a layer above this tropospheric layer. The great red spot is white because that bulges above the underlying atmosphere. And so you get more reflected sunlight there. And then at the top and the bottom, you can see red, and that is the aurora. You can see this auroral signal here looks very familiar to me because this image on the right here is the ionosphere. So unlike Earth, I think, Jupiter has this amazing confluence of two different things. One is that just like Earth, there's greenhouse gases that absorb a lot of infrared. And so in the infrared, the planet actually starts looking darker and darker. And so you can see that while in one wavelength, we've got this lovely reflected sunlight, in the green, it's very, very dark and there's not much information at all. And in the red, there's almost no red. That's because those greenhouse gases start absorbing. And you can see in the image on the right, you can see almost nothing away from the pole because those greenhouse gases in the depth of the planet have just removed all the light completely. Sunlight hits it and just gets trapped. And instead, the only thing you see is the hot glow of the top of the atmosphere. So it's a thin transient layer. As the atmosphere gets thinner and thinner, the equivalent of Earth would be somewhere around 100 kilometers up. So on the fringes of space, basically. But if I play this movie, hopefully it will play. It was just playing. Well, that's annoying. There we go. This is a set of data taken with the same telescope as we're using today, where we're able to image what the upper atmosphere and the aurora look like. And you can see over a period of a day that aurora rotates around and around, and there's lots of auroral activity. And so that layer is sort of sitting on top of what you see on the left-hand side. These images were amazing, but not really able to pull out this specific information just because there's always some reflected sunlight unless you get to a really, really narrow filter that's specifically designed.
For the benefit of the audience, I was wondering, do you want to tell people how Jupiter is, say, so different to the Earth generally? Because even the starting point is so radically different from our own planet.
Oh, sure. So, I mean, the most obvious radical difference is in how we describe these two worlds, right? Earth is described as a terrestrial planet, meaning a rocky planet, similarly to Mars and to Mercury and to Venus. All of these worlds are basically made of silicates and ions. If you stand on the surface of the Earth, that immediately tells you that you're on a rocky planet, and that the bulk composition of that planet is relatively heavy elements, basically. Whereas the giant planets are gas giants. They're all made primarily of similar stuff to the sun. So although they are more enriched with the heavy elements that make up the Earth, they are still dominated by really light elements like hydrogen and helium. And so for Jupiter, even though it's enriched by maybe 2 or 3 times the sun's composition, it's basically a big ball of hydrogen. And so there is no surface. There's nothing to stand on at Jupiter. All you would do if you fell into Jupiter would fall deeper and deeper until the pressures started getting so high that it starts changing in its compositional state. So you would end up in a situation where you would have a metal-like composition, but those are unimaginable to us. Basically, in any layer where humans could hope to survive, you're going to be moving through an atmosphere. And so that has a big change in the processes of what happens. And that's why you get these really significant bands of atmosphere, because those go as deep as we can measure, basically.
Give us a sense of scale as well, Tom, about
the
planets.
The other thing about the naming of these planets is that they are giant planets. They are very, very large. You can see the Great Red Spot. The Great Red Spot is about 2 or 3 times the size of the Earth. So the Earth would fit very well inside of here. So it's an enormous scale. It's a diameter is 10 times that of the Earth, and the mass is vastly larger. It's about 300 times the mass of the Earth. So this is a huge body. It's not quite large enough to be considered a star. You have to go up an order of magnitude at least until it even starts infringing on the space that we might describe as a star. But it's basically a star that's so small that it just can't fuse anything in its core. And so it's this huge wash of gas and dust, whereas what we are is effectively the Earth is just this lump of material, much more like an asteroid or some other rock in space that hasn't been able to accumulate very much gas around it. So in the heart of Jupiter somewhere is an Earth-like rocky core, but we don't know how big it is because it's almost impossible to get a measure other than through models. It may be the size of the Earth, or it may be much larger. We don't know. So this is a very different world in many ways. And similarly, there are similarities. There are startling similarities. So yes, the Great Red Spot is very, very long-lived, maybe 200 years. We were talking about that with specific examples from the RAS library on Thursday. Maybe 200 years, maybe more old, but it still looks very much like a cyclone or a hurricane on Earth, with that kind of atmospheric weather, vortice. You can see the bands. There's more bands at Jupiter because it spins faster, but the atmosphere has those same bands as the Earth's Hadley cells. The aurora is very different in many ways, but the fact that it has an aurora is because it has a magnetic field generated inside of it, just like the Earth does. And
so even that aurora there is several times the size of the Earth on that scale.
That's right. Yeah, the aurora itself is about 2 or 3 times the size of the Earth at least. And if we were to put the Earth on here, the aurora would be relatively small on that as well. So some of these features are bigger than the entire aurora of Earth, and we barely resolve them from Earth. So it is a very different scale that we're talking about. So
I'm just going to
helps us view it, from.
I'm just going to bring in, I think it'd be good to bring in Henrik, Melin and Paolo Taranti, sitting patiently in the other window, and they're actually, they're collaborators with Professor Stallard, and they're, rather than at Northumberland, they're in Leicester. So guys, I don't know if you want to come in and add to what Tom's been saying.
Yeah, I mean, Jupiter is awesome, and it's awesome to observe as well, because the aurora is incredibly bright because it's so powerful. There's saying that there's more energy being produced in the aurora of Jupiter than all of the power plants on Earth combined. So there's a huge amount of energy producing this glow. which makes it bright and therefore quite easy to observe from the ground using telescopes. And as we'll probably see later, we observed last Thursday with the James Webb Space Telescope. It's the largest, most complex space telescope ever built, and it was designed to look at the first galaxies in the universe, objects that are extremely, extremely faint. And what we do, we're pointing this very sensitive telescope at one of the brightest objects in the night sky. And actually the aurora is so bright in some of the frames we got that it actually saturates the instrument. So that's kind of the power we're dealing with here.
So by saturation, you mean it's so bright that essentially almost whites out the detector. Is that right? That's
right. Yeah. I'll note that it's okay though, and the detector's not in danger or anything like that. It's expected behavior, but yeah, it's really, really bright.
So I don't know if the three of you want to say, the thing that distinguishes this one from last week is the fact that we've got this new James Webb Space Telescope data. So are you able to show us some of that as you move through? Or
certainly can. I don't know if you want to do that, Henrik, or shall I open up that set of slides that I had?
Yeah. Let's see. I want to show the preview, some of the preview files that I did.
Yeah.
So our program scanned the limb of Jupiter clockwise going around the planet. We have 36 observations, which will cover all the latitudes. Unfortunately, 5 of those observations were not, well, they didn't happen because there was a problem with the guide star. So we have 31 observations, but they look absolutely extraordinary. And I've been lucky enough to been processing these observations over the weekend. So it's kind of cool. You're the first person to see this data, and it's kind of stuff certainly I live for. I think it's great.
Absolutely.
That's a great expression. Paula, I can see you're smiling as well. Do you want to add to this? Tell us what you've been doing with the work.
Yeah, we've just been working together, and probably they aren't the images you would expect, scanning all of the planet as usual, but as Henrik said, it's just on the limb. So let's say the contour of the planet, but it's good because we aim to look, as they said, at the aurora, but also at lower latitudes emission. So because the aurora is very bright at the poles, we try and really look for the very, very, very faint emissions at lower latitudes. Just a bit like seeing this sort of aurora or like northern lights in Mexico or something, but yeah.
So now I can see or we can see the 3 images you have there, and I think they'll certainly need some explanation, because bearing in mind, we've got a lay audience and so on. Probably everything from the wavelength you were looking at through to the kind of the use of the color scheme, what you're seeing in the grid lines and so on. So tell us what we're seeing here. I mean, I can see obviously images in green, reddish, and purple.
Yes. So firstly, the image at the top right is meant to orient you where we're looking at. So those red squares is our field of view. So we're observing a really small part of the planet. So this was our first observation, and we chose this location on the planet because Juno is flying behind the planet, taking observations of the ionosphere as well. So
Juno is a Jupiter space probe.
Yes, that's right. It arrived in 2016 and has been doing tremendous work, looking a lot at the magnetosphere and things, that the processes that generate the aurora and things like that. So within these images, there is actually, well, Juno are in these images effectively. So Juno is flying somewhere in these images. You can probably work that out. So what we're seeing, so the data we get back is 3-dimensional cube. So you have two spatial dimensions, X and Y, and you also have a wavelength dimension, and you can pick certain wavelengths and make an image at that wavelength. So on the left, you can see clouds at Jupiter. They're at 3 microns. So the lines are latitude and longitude, and they're labeled as well, just to give us a sense of where we are
Tell us what, when you say 3 microns, that's just in the near infrared, right? So just beyond the red end of the spectrum, we can see with our eyes.
That's right. Yeah, we can't see these wavelengths with our own eyeballs, and so we need an instrument to do that. So I picked the clouds specifically. It could give us a good sense of where the planet actually is. And I'm quite amazed that the pointing of James Webb is so incredibly accurate. This is exactly where we wanted the observation, and it is exactly what we got. So spot on pointing by James Webb. The middle panel in red shows basically deep thermal emission from the planet. These are the remnant heat from the planet is collapsing very, very slowly, constantly, and is releasing huge amounts of heat. So that's seen as the red stuff. However, there's also clouds on Jupiter at these wavelengths that sit on top of this heat. And so where it's dark here, the clouds obscure the thermal emission. So where it's bright red, there are no clouds, and we can see really deep into the atmosphere. Where it's dark, there are clouds, and we can't see deep. That's the 5 microns, even longer wavelengths. On the right there, we have emissions from the ionosphere, and that's the molecular ion H3+, and that's basically a lot of what we do is observing H3+ on the planet. It's one of these ions that's produced, well, the atmosphere of Jupiter is mostly hydrogen and molecular hydrogen. If you ionize, basically remove an electron from H2, you end up with H3+. So H3+ is the dominant ion in the ionosphere. And so that's what we're seeing here on the right. It's not a lot to see. Well, there is structure in here, and I think that's very interesting, and Tom's going to talk about that a bit later. But if we move up, so this is the first out of the 31 observations, so we can move up towards the pole, like there, for example. We go back one, Tom. That one there, as you can see, the aurora is now coming into view on the right there, hugely bright. You can also see a spot right in the bottom third, bright spot. That's the Io spot. So that's emissions, the particles coming along the field lines from the moon Io, and they impact the atmosphere, and they create a small increase in the ionosphere right there. And there's a trail, it's a tail that goes away towards the right as well. It's an Io trail. So we're really lucky to capture this in the first instance. We really weren't sure we were going to get anything like this. So that's kind of cool. We can look at the Io spot. Obviously, we got the aurora and things like that. If we move even further up, we can see structure within the auroral oval. And you can see with those pixels that are saturating as well, really bright stuff on the limb. It goes a bit funny. We're hoping to fix that in the post-processing. I mean, we only had this data for a few days, so it's still early days. But
we've got a whole suite of H3+ lines. So the brightest ones are the obvious ones to use to map out the non-auroral areas, but there's plenty of weaker emissions that we can fill in there.
Do you want to say what H3+ is?
So it's the simplest. I'm parroting my supervisor from 20 years ago. It's the simplest polyatomic molecule in the universe. Basically, all molecules are made. All molecules and atoms are made up of protons, neutrons, and electrons. That's the core of an atom. And you take the simplest atom in the universe, which is hydrogen, and it has 1 proton surrounded by 1 electron. The electron is negative and the proton is positive, so a single hydrogen is neutral, but bonds really well with another hydrogen for chemistry reasons. We don't like chemistry because we're physicists, but it happens. You get 2 hydrogens stuck together, it's incredibly stable. But if you hit that neutral molecule with something really energetic, and it can be energetic light like EUV streaming off the sun, or it could be an energetic electron streaming in from the surrounding space, you basically knock away one of those electrons, which creates something incredibly unstable because you have 2 protons and 1 electron trying to hold it together. So they're trying to force itself apart. But in Jupiter's atmosphere, you very quickly hit more hydrogen. It steals a proton back. And so then you're left with 3 protons and 2 electrons. And that's somewhat unstable, but is able to hold itself together if it jostles into hydrogen, is actually one of the most reactive species in the universe and is really useful for explaining a lot of the chemistry in interstellar space. And in fact, we wouldn't be here. Planets wouldn't be here probably without that, because it's needed to engender that chemistry and produce gas clouds that ultimately led to the production of stars and planets. So it's an incredibly important molecule because it's hugely reactive. It can react in almost any condition. One of the few conditions it can't react in is if there's nothing except for hydrogen around. And so at the very top of Jupiter's atmosphere, the weight of larger molecules like methane is such that they've settled out and fallen to a lower layer. And you've got this very pure layer at the top of the atmosphere that's just hydrogen. And then you're zapping that layer with all of this aurora. So it's a perfect laboratory to make H3+. It's one of the few places you can make it. It's really hard to make it in the lab, because if you're in the lab and you're trying to measure it on Earth, you get these contaminants and they remove it. Whereas Jupiter's this perfect place just at the top of the atmosphere that you just make bucket loads of it and it can't be destroyed very easily. So that's great for us because we're interested in, we're interested in the molecule as well, but we're interested in what makes that molecule. Is it that energy coming in from the sun? Is it the energy coming in from the surrounding space environment and all of that precipitation from surrounding space? And what destroys it, and how do we see it? The other thing that's really important about this is that because it's jostling into the neutrals all the time and not getting destroyed, it takes on the thermal characteristics of that neutral. So because the top of the atmosphere is hot, just like the Earth has a thermosphere that's hot, this molecule gets very hot and glows very brightly. So we can see it really clearly. It gives us a measure of the conditions of the neutral atmosphere in terms of the temperature, and it tells us about all of those processes coming in. And that's why this is really important, because it gives us this full measure of what's going on. So it's a ridiculously bright signal that we're looking at. That the image that you can see here is cutting out because this is one of the few objects you can observe from Earth through clouds. It's so bright that it just shears through all of that. It seems ridiculous to use the biggest and most sensitive instrument in the world to do that, but we're not necessarily as interested in this really bright aurora. It's all of the stuff that's happening around it. So especially down on the equator, it's really hard to do these observations from Earth just because it's 100 times weaker, and you can't sit and look at something for a long time. That's the way that astronomy usually defeats the problem of something being not very bright. You just look for longer, but the planet's rotating. It's highly dynamic. There's lots going on. So if there's any variability, you lose that variability. And on top of that, you're faced with the issue of just being able to track on an object and being able to integrate for any amount of time is really hard. And so all of those things contribute to the need to be able to take very, very good data very fast, which we've been trying to do with telescopes like Keck, and to some degree have managed to do that with Keck. But what we also want to do is, in this observation specifically, is look above the limb. You can see that on the left-hand side, you've got the glow on the limb of the planet from just the clouds just below this white line. But and then the same from the thermal. So this is the heat coming from deep down, and the dark bits are where clouds are in the way, and the bright bits are where they're not. And so you're seeing the glow from the interior. But when you look at the aurora, you can see it's well above that line. It sits about, 500 kilometers above the surface. That's what we're really interested in.
So I know it's early days and you've just had this data back, but from the three of you, any surprises so far in them?
I mean, well, there's different levels of surprise, right? Because we didn't know where the positioning would be. having the great red spot like this is, the Io spot and tail that Henrik described here is really amazing, because we didn't think we'd be that lucky. It's really good that we've gotten that. That we have got better constrained, like, spatial images of that spot before from Juno. So Juno has these amazing images looking straight down on it. But the instrumentation on Juno is intrinsically limited because it had to get all the way to Jupiter. And so the level of spectral detail in those observations is pretty low. So I think that this is probably the best measurement of the Io spot ever taken, where a good temperature measurement of the spot can be made. So that's really good. And you can see we have two separate frames too, which allows us to view that on a different scale. The fact that we've just got this long run through, you can see this beautiful scan. There's a little jump here, which is what Henrik was talking about, that we lost the guide star. And so hopefully we'll acquisition those again later. As you move around, there's all sorts of weirdness in here, and I can talk about that in a bit more detail later, but you can see that we've got this wonderful view of what's going on, lots of dark stuff. I would, for instance, here, it seems to get brighter. That's just the automatic scaling that we have. You can see the back on the right-hand side, there's some noise that we need to get rid of, and that noise also gets brighter. So a lot of these images, it's hard to see what's going on, but they all have this kind of level of brightness, and there's some amazing stuff in here. These very small scale features are something that Henrik saw in an earlier observation, but they're very weird, I think, is the easiest way to describe it. I can't really explain what that means. Weirdness is not a very scientific term, except for the fact that we have no real constraints on what scientifically we should describe these things as. Certainly in the past, we've seen some straight lines in this data. I don't think in the past ones we saw anything like this weird dark thing here. Some of these features we can explain, and I'll talk about that in a little bit, but this blob here is unknown to us in the past. There's no way of us knowing about it, really, because it's so small and so small scale in terms of the brightness difference as well. But things like this are just hard to explain. What would be really useful, and maybe we can try and work towards, is knowing whether this, if we'd looked 5 minutes later, whether that would be in the same place, moved, or disappeared. It could well be that that's always there, and it's a very small scale feature, or it could be that it's some form of wobble in the atmosphere that we're only seeing temporarily frozen. And I think once we start stringing this data together, you can see that on the limb, we're actually getting regions where we're covering the same part. If I go back to the eye, you can see that. You can see as we cut through the aurora, we're seeing the same regions in multiple frames. So that should help. We should be able to try and stitch things together better as a result of that.
So can I ask, how long does it take to get each image here?
So the observation was the total observation time was about 22 hours, but nearly all of that is positioning, checking guide star, all of that kind of stuff. So the actual total integration time on the planet was about an hour and a half, so 90 minutes, and we had about 30 or so observations. So it's a couple of minutes or so. Henrik has the specific details of how long we did it for. But
Henrik,
he's busy, maybe.
Yeah, sorry, we're setting up the IRTF. Observing.
So you're setting up for the connection to Hawaii, is that right?
That's right. Yeah.
Excellent. So, okay. Well, we'll go to you in a minute, I guess, and when you're ready to come in. But
yeah. So it's giving us this kind of window, this beautiful view of what's happening in the planet over a whole wide range of wavelengths. So obviously what we're interested in is what we've been describing, the top of the atmosphere, but you can see that there's thermal emission deep down in this data. There's atmospheric clouds. We have collaborators that are interested in the stratospheric chemistry. They're interested in hazes above the limb of the planet and on the body of the planet. They're interested in weather systems, and all of these scientific questions can be really greatly benefited just using this exact data set, basically. So we're in contact with quite a lot of people that are obviously very keen to see the data, because there's so many different kinds of science that you can resolve with this. It's a fundamentally breakthrough piece of information that we have. It's a new window, just because it combines a view in detail of the planet with incredible spectral detail that you cannot take from Earth, because the Earth's atmosphere gets in the way, and you can't take from in situ around the planet because you can't build an instrument that's good enough, that is light enough that you can launch it to Jupiter, basically.
Right. So do you plan, I mean, I know that in the past, I think, Lucinda, you were involved with Lucinda's previous webinars looking at things like Uranus and so on. Do you plan to make similar observations of the other gas giants?
So some of those observations have already happened.
Right.
The early program, so obviously before launch, there was a lot of interest in how do we get the very best science as soon as we get going. All things going well, we will arrive and the telescope will switch on and start being able to observe. So there was a concerted effort to make sure there was a huge, rich program of observations that we could take as soon as the telescope switched on. And some of those were a range of observations of the different planets with different instruments. So we have had observations using this wavelength at Uranus and Neptune, and none of that has been published yet, but someone is looking at it, probably someone on this live stream. Yeah. And so there is work being done, and it's getting closer to publication. Jupiter, there have been a couple of observations since then, because they had a pre-bid, the early release science program, where scientists could actually say, this is what we want to look at. And Henrik and I were part of a much larger consortia to look at Jupiter and Io as well, some of the moons of Jupiter. And we looked at the Great Red Spot, and we looked at the aurora. So that's also in process of being processed. One of the big outliers for us is Saturn. Saturn was observed both with images and with a different wavelength, the mid-infrared, so further along than this. But as far as I'm aware, no one's ever looked at it using this instrument. And for us, that would be hugely useful. We've asked to do that in the past, and we have not yet made a convincing enough case in a telescope that's oversubscribed by 10 to 1. You basically, for every one amazing observation that gets taken, there's at least 8 or 9 really amazing observations that could have been taken and just were deemed to be not quite good enough. And that's the reality of it. This observation that we took is an amazing observation, but it wasn't the only planet observation that was asked for. There was a whole slew of observations of different planets and different scientific targets that we all put in as a community, and this was the only one that was picked that year. So that's not to the detriment of our science. It's because we've also got huge numbers of people asking for exoplanet observations of galaxies, and of course, some of these early targets observations, which are changing our understanding of the universe, which is probably pretty important too. So that's the way these things work. We would love to have similar observations to this for Saturn, but partly because we struggled so much to do that with Cassini. I was very much involved in Cassini observations of the aurora, and we could get very nice auroral images from the instrumentation on Cassini, but it was on the edge of detectability. And then as we moved down away from the aurora, it was just too weak, despite years of us trying to eke the data out to get some signal off of the planet. It was impossible. We have done it from Earth, but it's very irregular. So using the Keck telescope, which is one of the telescopes we were using on Thursday, we have measured all the way to the equator and seen this signal once or twice, but we've looked again and it's gone. And so it's right on the very edge of detectability. So we know there's all sorts of fascinating things happening. It would be great to be able to see those in this kind of detail. So we'll keep pushing for that, obviously. But yeah, we're very lucky to even have this. And we've just heard that a colleague of mine, Johnny Nichols, has got more time looking at the aurora of Jupiter because he's put in time for Hubble Space Telescope and has a linked observation for James Webb. So he'll be looking at the dynamics in the UV because there's a beautiful bright aurora in the UV and comparing that with the infrared. So it's this comparison. So he'll be able to look at, I think, the same time with 2 space telescopes, which is, you know, amazing. So that's kind of where we're at in terms of the stuff that we're looking at right now, but it's all very fresh in terms of the data. I'm happy to talk about some of that, and maybe we'll come back to it, but we are starting to get set up on
I was going to say we should I'm looking at on my screen at Henrik and Paula and wondering when it's a good time to switch over to those guys. Are you ready to talk to us, Henrik?
Well, what we can do is I can talk through what they're doing while they're doing it, because I can actually show what they're seeing on the screen.
I was going to say that would be really useful actually if we could see how your connection to Hawaii is.
If I just share the full
Probably need to share
screen.
your screen, do you, Henrik? Or
I can share it.
oh, can you, Tom? Okay.
Yeah.
Great.
So the way the telescopes now work, and IRTF, the telescope we're on, was actually probably the leader in this. They were doing remote observations like this in
Tom, tell us a bit about IRTF, you know, how big it is, how it looks at the sky, where it is, all that kind of stuff.
Let's have a look. I will pull up a lovely picture of it. Give me a second.
I think, yeah, for the benefit, again, you know, most people probably on the call, well, unless there are people on the call who have time as well, but I think the majority probably won't know.
So IRTF is one of the oldest telescopes on Maunakea.
Maunakea is an extinct volcano on the big island of Hawaii, isn't it?
That's right, yeah. So why build a telescope in the middle of the ocean in Hawaii? It sounds like a luxurious place to build a telescope, but there's a very good reason for it, which is that in order to get the very best observations you can, what you want is incredibly clear and as thin as possible air. You want low turbulence, low water content, and you want it to be very stable. And so there are some very good telescope sites on mainland locations, especially the Atacama Desert's very good. It's especially good because it's so dry. The Atacama Desert's one of the driest places in the world. Let's see. This is a lovely picture of IRTF. Here we go. So this is the IRTF on the summit of Maunakea, looking out towards Maui. It's an interestingly shaped telescope because it has this square base, so it's very easily identified whenever you see images of the summit. And for scale, you can just about see a car down in the bottom left corner here. So it's a pretty big building, even for such an old telescope. There's 13 telescopes on the summit of Maunakea now, and it's one of the oldest. It was built in the 70s. Specifically, it was built out of the pocket change left over from the Voyager mission. So the Voyager mission cost billions. They had about 100 million left over. This is the classic story. Whether it's true, I don't know. But they had about 100 million left over, so they built this telescope on Maunakea specifically to support planetary observations. So that's what makes this telescope particularly unique. Nearly every other telescope in the world is focused much more on observations of the whole of space, and typically that will be very different style of observation. So nearly all the objects in the night sky are fixed, effectively, at least on human timescales or observing cycle timescales, they don't move at all. Whereas the planets zip around, as some amateurs watching will know, that they can be quite hard to find sometimes because they've moved so much over a few nights.
And this one is what, 5,000 meters above sea level or something like that?
So it's about 4,000 meters above sea level. You can see the cloud deck well below it. It's not so high as to be completely intolerable to humans. It's sort of on the edge of tolerability. It's still quite an experience to observe there. It's about 60% oxygen when you're at the summit. It's one of the few telescopes where you still can observe from the summit these days. The world has changed, was already changing, but the pandemic has absolutely changed observing, so that nearly all telescopes now only typically run either by having a queue system where someone does your observation for you, a professional astronomer at the site will do the observations, or you do the observations remotely. And IRTF is sort of ironically one of the last that you can observe in situ, because they were one of the first to allow remote observing. So back in 2000, they did some of the first remote observations. That's a very long time ago now. And so what you can see behind this image is two windows. And these are the two windows that Paula and Henrik are using to do observations. You've got on the left-hand side here is the spectrometer. That's the sort of science bit that we're really interested in. And the right-hand side over here is the imager. Right now, we can't see anything particularly interesting because we're taking calibration data on a star. So you can see in the imager on the right-hand side over here, there is a view of a sort of area here, which is the width, the imager itself, and then a flat line inside of that. That flat line is the spectrometer. So basically, we're looking at part of the instrument which has been polished, and there's a hole in that instrument. The hole lets light through, and that light gets split up into wavelength components, just like a prism splits light up. And that's how we get some really interesting science out. So the interesting science bit is on the left, which is not necessarily very accessible or interesting to people looking. You can actually see in the data on the left-hand side here, there's this black line and a white line. And that's because the atmosphere is so bright at the wavelength that we're looking at. The Earth's atmosphere is so bright, it's hard to look through. In fact, you can see up here, it's very, very bright here. And so we're basically looking at the star in two different points on the slit. And so these are two different observations subtracted one from the other. So we're removing the Earth's atmosphere by taking two observations, subtracting one from the other. So we get a big bright positive, a big bright negative for the star itself. And all of that bright Earth atmosphere gets removed. And this is just a calibration to tell us, well, how bright is everything? We're measuring, the number of photons we're looking at. And so in order to get from photons to an absolute brightness at Jupiter, we look at a star like this, where our understanding of the physics of how stars work tells us exactly how big that star is and how bright that star is. So if we measure the brightness of the star in the data, we can say, well, that means this energy, this power for the star is equated to this number of photons. So there's 1,000 watts per meter squared per micron is the equivalent to 88 photons. And so we can scale that to look at Jupiter and then actually understand how bright Jupiter is. So it's something that we always try and do every night, because we're observing, because it gives us that absolute measure. And nothing is happening right now, which means that we're going to Jupiter. So right now, the telescope operator has taken over, is slewing the telescope from this target over to Jupiter. And the first indication you will have of that is on the right-hand panel over here. Once they get to the position of Jupiter, they will change the basic settings, and then we'll hit go on the imager, and you should hopefully now see Jupiter appear. Let's see if I'm right. There we go. So that's Jupiter right now.
Remarkably easy there. Well, seemed that way.
So very bright view of the planet, which is very similar in wavelength to some of the stuff we saw in the classic picture, the one that you have behind you. You can see the glow on the north and south is very similar to the James Webb image. The detail level is obviously much lower partly because we're looking through the Earth's atmosphere, which jostles and makes everything less smooth. Even a site like Maunakea in the middle of an island with very smooth, clean air blowing across it, we still get some distortion from the Earth's atmosphere. But also because, scientifically, this is not what we're interested in. This is just a way of finding where we are on the planet. And actually, this is how we make sure we're positioned correctly. We can use the planet to guide on. So basically, the panel you see on the right is both an imager and a guider, and it will use that image itself to guide. It's one of the things that makes IRTF really good. Most telescopes can guide on off-axis objects like stars, but stars move relative to Jupiter, so it's very difficult to get an exact rate that works and follows exactly where you want to be on the planet. We can use the actual data coming in from the planet itself to guide with. So we take the bright poles and we run that through the guider. The guider figures out a sort of central point and matches that.
So Tom, again, for the benefit of the audience, why perhaps you could say why telescopes have to guide and track?
Well, okay, so
the object they're looking at.
There's two different reasons, right? One reason is if you're looking at a planet, it's moving through the night sky. So you need to account for that correction. You can do it with rates, though. You can actually calculate mathematically using celestial dynamics what the rate of the planet across the sky should be. But the telescope itself is a giant piece of metal, and that metal is heating and cooling, and it's a very delicate balance. You try and balance up a telescope properly and counter all of those flexures, but you can have very small scale flexing, micron level flexing sometimes is enough. Because we're zooming in so much on the night sky that we see Jupiter so big, it can cause huge problems in terms of making sure that positioning and your tracking wheels are tracking properly. There's no end of ways that, because you've got this enormous piece of metal that you're trying to make follow the sky, that it doesn't just drift off in some very small way. And these inevitably will drift off to some degree. Even the very best telescopes with perfect gearing will ultimately have some kind of issue like that if you leave them long enough. So you can correct for that by hand if you can see the image. And sometimes we have done that where we've, certainly in the olden days, the bad old days when I was observing a couple of decades ago, it was all done by hand and we just had to try and keep the planet in the right place. But these days, you can guide in a number of different ways to try and counter that and correct for the fact that the telescope's distortion as it moves around and as it heats up and cools down flexes where you're looking at. But doing it in situ, using the images, is profoundly beneficial, because then you don't have to worry about differential tracking rates or differences in how the instrument's flexing between those different targets or whatever else might cause distortions to that. And you as the user have complete agency on it as well. So it's up to you to figure out when it fails and correct for it, but you can correct pretty easily. So right now they've set the instrument guiding using the planet itself. So they're taking a sequence of images once every 1.5 seconds. They take an image, that image appears, and then in the bottom right panel, you can see these 4 images here. This bottom right panel here is actually what the guider is seeing. So it's deciding where it thinks the center of this is and repositioning the telescope so that the center always fits in the same place. And so by moving the box around, we're moving the planet around until it's in exactly where we want it. So these scans are happening from the top of the planet to the bottom, unlike James Webb, which went like a clock around. We're just going straight across the planet from pole to pole. I can show some of the results from past nights that we've been putting together, we've now gotten this really nice catalogue of different scans through this region over different nights. The aim there to be checking the temperature of the neutral atmosphere. So by measuring the temperature over multiple nights, we're hoping to see variations. We know that when we've looked in the past, there's been very significant changes in the temperature at the equator, sometimes by up to 50% hotter, maybe even more some nights. So something is heating the equator up, and that's a huge question that we would like to resolve. Our colleague James O'Donoghue had a paper out in Nature about 2 years ago, which appears to have solved that issue, because we saw huge waves of energy appearing to pulse from the aurora down to the equator. So that auroral temperature is very constrained by the fact the planet spins. And so it sort of blocks, the Coriolis force blocks that heat getting down, but it appeared that it was washing down. This is our attempt to resolve that with this observation. If we look for a month and we see the aurora get hotter, and then we see the equator get hotter as well, and we will know for sure that that's the source of this heating. So it's a fun experiment. That means that we just have to observe lots and lots, which is always what we like to do. We love to observe lots and lots.
So Henrik Powder, is there anything you're expecting from this observing run, I should say, tonight or today?
I think they are busy talking to the telescope operators right now.
Are they really? Okay, yes, it looks like that way.
So
yes,
they're on two different streams. Or maybe they're trying to speak to us and can't because they're
not muted, and still muted. Yeah, that's a good question. Yeah. I don't want to disturb them if they're in the middle of
if they're about to pop up. Maybe not. On Thursday, I was on 2 separate telescope Zoom calls as well as this call, and it's the most confusing thing I've ever done. Having to mute and unmute every time from 3 different calls was pretty horrific. They're on, I think.
Talking to both the team in Hawaii and an audience here. So go for it, guys. You're obviously unmuted now.
So we're just started observing Jupiter using the IRTF instrument called iShell.
Did you get the 1 times 3 or the 1 times 1?
Sorry.
Yeah, we can continue.
Sorry.
That's okay. No, it's quite fun for people to hear the dialogue actually.
So I think that was my student Katie Knowles observing from Japan.
Okay. Oh, right. Okay. You see, this is the multinational. If you ever wanted a demonstration of the multinational nature of astronomy, we've got people, in Leicester and Northumberland, and me down here in Sussex. It's not quite as exciting as having people also in Hawaii and Japan as well, as you know.
Yeah. So Katie is the person that actually put the proposal together and was awarded the time. So this is very much her baby, but we've all been working towards making sure this gets taken, because as you can imagine, a month-long series of observations every other day does get somewhat debilitating. I tried to do it. I tried to do the whole month, and about 2/3 of the way through, my brain broke. I couldn't keep going because
How long is it each run typically when you're getting that?
So I mean, each night has only been 2 hours, so it's not impossible. And I've had much harder observations before in some ways, but it's the cadence of every other day. There's not enough time to drop it from your mind, but it's sort of sitting there lingering. If it was every day, it almost would be easier because you'd get into the rhythm of it and not have a break. But yeah, it's pretty hard. And so on the left-hand side over here, you can see some very bright lines have now appeared on this array. That bright line there is the H3 plus that we were talking about. It's just part of the spectrum, and that's up near the limb of the planet. So we're seeing really bright signal. I can just scale that. You can see wonderful lines there. So that's what we're interested in. James Webb is amazingly sensitive, but it's not as good at splitting the light into its component parts. It has a resolution of about 4,000, which means that if you divided the wavelength that you're looking at up into thinner slices, it can go 1/4,000th as thin as the wavelength you're looking at, which is great. It really lets you see the individual lines that you could see in that data very well. But the negative is that it's not able to do certain science. So even James Webb, with its amazing power, is still bettered by a 3-meter telescope on Earth, because the instrument taking this data is about 2 meters by 1 meter in size. Cube is a huge cube. You can put in so much more in terms of the instrumentation.
I'm not going to quote you on saying that it would be better to buy a 3-meter telescope on Earth than James Webb, but
that's not what I said. If you want to do measurements of the winds of the ionosphere, then it absolutely is.
Yeah, that's a very specific and necessary clarification.
Exactly. So, some of the science that we do is looking at the winds. In fact, Rosie Johnson talked about that in the last live stream. It's the kind of science that you have to have a certain very narrow resolution. And this instrument is one of the best in the world for doing that. So even though it's a relatively small dish, the aurora is really bright, and we're able to get that signal.
And I think also what you're describing, I mean, there's that complementarity between space and ground-based and space probes, and it's only the three together that really give you the best picture, right?
Yeah. So to take a single frame that we looked at in the data from James Webb with that level of detail, I think would take, we were saying it's about 2 minutes. I think it would be about 2,000 minutes. So on the order of more than a full night on this instrument. It's not quite true, because this instrument's really amazing. And so we get a huge number of different lines that we can use, and the background is much weaker on these because it's so well stratified that it sort of fights back a bit and gets back a little bit of that lost complementary time. But the sensitivity on James Webb is just insane and crazy. And of course, there's some aspects of this that you just can't do, because if the Earth's atmosphere absorbs, so certainly it's wavelengths a bit higher than you can see here. Basically, the Earth's atmosphere eats it out completely. We see nothing. And if you have anything in that wavelength window that you want to look at, you have to go to space to see it.
One of the things I was going to ask as well, actually, I was just thinking again, for the benefit of the audience, perhaps you could say we talk about terms like wavelength a lot, and just that sort of differentiation, because I think most people will probably be familiar with infrared, and they'll have seen it from things like, I don't know, demonstrations of firemen's cameras, fire officers' cameras, and so on. But you won't necessarily, the concept's not always clear, and let alone the tiny numbers you're talking about in terms of those waves.
So, I mean, there's a world to enter into there about what is the duality of light, and the fact that it can be a particle and a wave at the same time. I'm not well placed to make that discussion, but let's just say that that's true, that light is able to be a particle and a wave at the same time. And that wave carries the energy of that particle, right? So the particle has an intrinsic energy, and that energy is defined by the wavelength of that light. So as you measure the line, it specifically has a length. So if you think about radio signals, radio has a wavelength of meters or tens of meters, and that's why it can move through the world so easily, because nothing can block it, nothing can get in the way of it, because it's such a long wavelength that it just sort of moves around everything. And then as you get to more and more energetic waves, you get to higher power. So dangerous light, things like X-rays, where we have famously, we can use those to look through the human body because they're so energetic, they can get all the way through, but that's also problematic if you're exposed for too long. And then even longer wavelengths than that, up to gamma rays. Gamma rays are insanely dangerous because they're so powerful, and they give off huge amounts of energy. But fortunately for us, that kind of really high energy stuff gets absorbed really easily by the Earth's atmosphere. And so we are protected from all of this mad light coming from incredibly energetic sources in space by the top of the atmosphere of the Earth. And it's exactly the same kind of light that we're seeing in these observations. Some of the light that we're seeing from Jupiter here is produced by the sun's bright light, but some of it is also produced by gamma ray bursts in the galaxies surrounding us. In fact, Henrik had a lovely little paper where he looked at using Cassini data as it flew past Jupiter at the day side and the night side, and he was able to show the same kind of brightness on the night side as the day side. So obviously the sunlight hitting the day side made it really bright, but even looking on the night side, we were seeing the same kind of morphology in the equatorial regions of the upper atmosphere, presumably because of gamma ray bursts and all of the other energetic stuff happening in the universe hitting that dark side of the planet and making it glow in the same way. So yeah, that's really high energy and then really low energy from radio all the way through. Infrared being relatively low energy, but you can make infrared very easily from heat. So the famous view of that is, you know, firemen's cameras are able to look through the smoke of a fire and see people underneath because the people themselves are producing the light from being hot. That's probably a longer wavelength than that we're looking at. But if you basically, the hotter the object, the shorter the wavelength it will be bright in, and so that's why it's why we see in color. Basically, the sun is brightest around the point at which our eyes can see. There's a window in the chemistry as well. The wave infrared is absorbed a lot by greenhouse gases, but in the visible, the light gets through the atmosphere really easily, and it's also the very brightest part of the sun's spectra. And those things in combination are why we evolved to be able to see in the visible. It's the brightest source that there is. So it's natural that in evolving, we've come to use that really bright measure. So there's a one-to-one link between the fact that the sun is about 5,000 Kelvin hot, and that the peak of that distribution of brightness is a nice window in the Earth's atmosphere. It's exactly why we see red, green, and blue, basically, because those are the three different kind of filters of color that fill in the kind of region that we can see with our eyes.
And again, at the risk of asking you to explain every term, can you just say briefly about what Kelvin are?
Okay, so Kelvin is a temperature similar to centigrade, but centigrade has negative numbers and Kelvin doesn't, because there's an intrinsic point at which the universe is as cold as it can be. And that's known as absolute zero. So that basically you can't get colder than absolute zero, because it basically means no energy and nothing's happening. So as you add energy to something, it increases the temperature, and as you take energy away, it decreases the temperature, but you can't take away no energy, and that no energy is 0 Kelvin or minus 238 centigrade, something like
73.
There you go. There you go. You can tell it's been a year since I taught this stuff.
I know it's so familiar as well, isn't it, when you use these units. I've actually got a question on YouTube as well. So this is from Randall Griswold, and Randall asks, does Juno's GIRAM instrument have the ability to view these ionospheric phenomena you're interested in?
It does. It's actually been built specifically to do that. The GIRAM instrument is a really interesting instrument because it is effectively sort of what you see in the right-hand side here. You see an imager with a slit in it, and the instrument itself has two different wavelength views. So it has a thermal one that looks at the hot stuff from in underneath, which is similar to what we see here. So in our observations from James Webb, this is the deep thermal emission. So one of the two images that Juno has is that, and the other is very much like the ionospheric H3+. It's a filter designed to just look at the H3+. So it has two images, one that looks deep and one that looks at the H3+, and then also has a slit in one of them, just like our imager has a slit, and the light goes into that and is able to measure the spectra as well. So it's produced these amazing images of the aurora, just really, really beautiful images, much more detailed than anything you can get from James Webb. and that's intrinsically limited by physics. You can only see a certain level of detail with a dish that is 6.5 meters wide at the distance we are from Jupiter. If you flew James Webb to Jupiter, it would be much better at doing our science, but not very good at anything else. Juno has been flown to Jupiter, so they specifically have put this instrument in place to try and get the best possible resolution there. But just like every other spacecraft that has flown to a planet, the ability to get that spectral resolution, the splitting up of light, is much poorer. It's 10 times more coarse in how it splits up light than the James Webb, which is usable and can get you some really useful stuff, but is a challenge. This is actually what Paola's working on right now. So she has been doing a lot of Juno measurements and trying to extract an understanding of the ionosphere of Jupiter using the spectral data that was taken. The images are just profoundly amazing and so much detail, but they don't give you physical parameters that we're interested in order to do that using the spectra. And so you're undoubtedly getting a higher spatial detail. You can see them in more detail, but not spectrally as powerful. And there's a lot of reflected sunlight in these different wave bands. You can see on the left-hand side here, we've got this lovely spectra, a detailed spectra of a H3+ line. So this is one of those emission lines, and you can see that surrounding it is very dark, but nearby there's some bright stuff. And so if you smear that out by 100 times, is how much smeared out GIRAM is. It's 100 pixels across or 200 pixels across in this image added together. Suddenly there's a lot of other stuff as well as the H3+ line that you're looking at. Whereas JWST is about 10 times smeared out. So if you crunch that down by 10 times, so you can see that James Webb is able to pick out a lot, but there will be some stuff from behind in some of the lines, whereas others of the lines, especially the one that's off down in the bottom corner here, is very dark. So it's this trade-off basically. And the balance point for Jupiter and Saturn, even more so for Jupiter, is definitely somewhere between 4,000 and 400, which are the two numbers for the spacecraft and for James Webb. James Webb is high enough resolution that we can really get some powerful science out, and 400 is having used a very similar instrument on Cassini for a decade, trying to get temperatures out. I basically failed to get temperatures out of the aurora for 2 years of work I spent trying to do it. I've got these beautiful figures to go into a paper, and it looked really convincing. And then I changed how I subtracted off the background very slightly, and all the temperatures changed. And that's not what you want from science. You don't want a very small calibration change to dramatically change your temperatures. So it's the biggest result I've dropped in my career. I spent years on it, and I just never felt confident enough to publish it, and I actually gave up and dropped it eventually.
One question we've got, which is not quite related to what we're observing today, but I'm sure you can answer it as well, is just, is JWST used to observe the moons of Jupiter as well?
It is, and has been, I believe. Part of the program for the early release that we put in were specifically observations of Io and at least one of the other moons, I think, and has been used in that capacity. I haven't seen the results from that yet, but there are people working on it for sure.
And what's interesting about Io, Tom?
Io is an amazingly interesting moon. Probably one of the most interesting objects in our solar system, I would say. Io is caught in this horrific conundrum where it wants a circular orbit. Jupiter's trying to make it have a circular orbit, but it is also surrounded by 3 other Galilean moons that don't want it to have a circular orbit, basically. So every time it orbits, it feels the kick of Europa and Ganymede and Callisto that drag it out from being circularized. But it feels the tidal forces of Jupiter just like our moon feels our tidal forces. So it's not a problem for our moon, right? There's only one moon, and so it has been circularized, and we see the same face of the Earth all the time because of those tidal forces enforcing it into a specific location. And basically, it's trying to become perfectly balanced with the Earth's rotation. So the Earth is slowly slowing down at the same time to basically smooth out all of this kind of gravitational friction, basically. And that's what drives the tides on the Earth as well. It's the oceans trying to match the moon, basically, in terms of its location. But because Jupiter drives vastly more powerful tides than that on Io, I believe that the average tidal range on Earth for water is something like 10 meters or 20 meters or something. And the average silicate rock tide on Io is about 200 meters. So the rock is being squeezed by 200 meters around and around as Jupiter goes around, but it can never settle down because of that kick that it's given by the other moons. So it's basically being squeezed and squished by Jupiter hugely. And that makes it massively volcanic. It's 80 times more heat flowing out of its surface than the Earth. So it's about 80 times more volcanic than the Earth. And there's no plate tectonics, which is a really nice way of getting heat out. Earth has this really efficient way of getting heat out. So all it can do is create these horrible blemished spots on the surface of hot spots, throwing heat out desperately. So it's this massively volcanic world where there's just these hot spots that fire stuff out. And it's a torrid hell as a result on the surface. It makes it really interesting for us because all of that stuff gets thrown out in these massive geysers that throw material out into space. And then that material gets ionized by the really energetic environment. And so it becomes ions that then couple with the magnetic fields that link into the planet that we're looking at.
Okay, I'm going to bring in just Henrik and Paula for a second, just to see if they want to add anything and tell us what they're up to there. I know I can see they're communicating with the operators in Hawaii.
Yeah.
How's it going, guys?
It's going really good. I think the weather is great. The sky is incredibly clear tonight. It's good. This is the last night of Katie's program. And we've been observing Jupiter on and off every couple of days for a month. And so there's the finale of that program. And it's nice to finish on a strong high, I think. So you can see Tom's screen there. We have Jupiter. We're scanning down Jupiter to measure the ionosphere from pole to pole. And we do that because we think it changes from day to day, depending on what's happening in the Jupiter system. So what's the volcanic output on Io? What's the incoming solar wind doing? And all these parameters. I'm trying to uncouple all of that stuff. We had a little issue earlier, which really confused me, but I think we solved it. It was fun observing it. Things happen all the time, and it's just how do you deal with those small issues happening all the time.
And and in this case, you're sitting in a room in Leicester, negotiating with an operator in Hawaii.
Yeah.
Have you both been to Hawaii in person to see the instrument, or only ever remotely?
I've been out before. Paula, you've not been, but we're going in a couple of weeks. We got some Keck observations, the 10-meter telescope observing Uranus. So very much looking forward to that.
Pretty amazing.
Yeah, I've not been out since pre-pandemic. So,
but it's a lot of things. Yeah. It's obviously a huge journey, and I suppose the other advantage, it is that description we had earlier, going up to 4,000 meters, all the adapting to the altitude and working efficiently.
Yeah.
Presumably not entirely unchallenging. So.
Oh God, no. No, altitude sickness is relatively common as well. Body just can't deal with it. It's not enough oxygen, basically. They have oxygen tanks up at the summit should you need them, which is nice.
So what's good for telescopes is not necessarily good for people.
Yeah, that's right. That's right. I think it's Subaru, the National Telescope of Japan, which is also in Maunakea. Don't they have the pressurized room?
That's an interesting. I don't know, and it's an interesting question, and we'll try and find out. We'll run this call, I guess. So.
So when you go to Hawaii and observe on the summit, normally you have to go to you stay in a place just slightly down the slope of the mountain called Halepohaku, which is like 3,000 kilometers altitude. So you acclimatize there for a day, and then you go up and work nights on the summit, which I think probably really helps. It's more difficult. But some people, hardcore people, go straight up from sea level all the way to the summit.
Not advised, is it?
Yeah.
No, I think certainly if you're driving or something like that. So
Yeah, we've had a few situations in our time that we've observed that's happened. One time on IRTF, an instrument exploded, which was not fun, and they drove very fast all the way up the mountain, understandably. I don't understand how they could do it. They are steely-eyed mountain men, let's say,
I suppose if you,
and women, but in that environment, doing that is pretty intimidating, I would say. But they are much more used to it than we are, because it's literally their day job.
So Henrik, you're a research fellow at the University of Leicester. That's right, isn't it? And,
That's right. Yeah.
and Paula, are you a PhD student or a postdoc? I apologize, I don't have your bio in front of me, so.
Yeah, no worries. Yeah, I just started my second year of PhD. So as before it was mentioned, the Juno gyram, I work with that. So data from Juno with the gyram instrumentation. So technically I'm not even meant to do observation from ground or go to Hawaii or anything. Well, because we all collaborate together, we have this grant to observe Uranus. So I have the chance to go, but technically I only work with data from satellite.
I don't think there's, I can see why you'd want to take that opportunity though. So,
Yeah.
So how much longer do we have on the access to the telescope today?
Another hour and 20 minutes.
Okay, so we should possibly leave you to continue with that for now, and I'll come back to Tom to talk.
Yeah, I just thought I'd show something of what we've been doing on IRTF. So I might stop sharing and just share this one panel because it'll be easier for everyone to see them. But this is a sequence of, so you can see on the left a typical scan. We actually have a really fun set of movies of all the different nights that we scan. But basically this is the kind of thing we're doing tonight too. We start on one limb and we move the planet upwards, and this hole here is where the light comes in. So the light goes through the hole, split out by a prism into its component parts. We pick out the stuff that is the top of the atmosphere from that, as we've been doing with these observations here, and can use that to measure what's going on. And so you can see around here is a whole slew of different scans. These are quick look images. Again, Henrik has produced these for us based on the individual nights. So this is 9 different nights where we've scanned through. We've got a few more since then. You can see the aurora on either pole. You can see that sometimes we scan through and then restart somewhere and do another bit of scan. So we scanned the northern aurora again here. So you can see these beautiful images of the aurora. In some cases, we're getting beautiful detail in the auroral region. A bit harder to see because of the noise, but you can certainly see in a couple of cases is the very dramatic changes in brightness away from the aurora. So over here on this side, there's a darkening and another darkening here. And then over here, we have a darkening, a series of darkenings away from the aurora. And all of those are caused by something. What is that is a big question for us. And I think until about 5 years ago or so, we just thought it was really boring in this layer and nothing much would be happening. And in fact, it's more dynamic, I think, than the aurora even in some cases. So this is what we can see from a moderately sized telescope on Maunakea. There's all sorts of wonderful striations and stuff. We're hoping to build that out and get an understanding of that. But James Webb is following the edge of the planet around this limb, and we can see those detailed images at much higher resolution because it's not looking through the Earth's atmosphere. So, you know, spatially, we can resolve the aurora in much more detail. but also just with a massively higher sensitivity. So here it's very noisy down in this equatorial region, and once we process the data properly with James Webb, we should be able to clarify that much more. But by doing this, there's different science that we want to get out from this. The one thing that we talked about was that temperature. So hopefully each of these scans will give us a temperature for the auroral region. We've measured the aurora in some way, and we'll hopefully see the temperature change. And sometimes it will be hot and sometimes it will be cool. And then we'll be able to see, well, how does the equator change? It might be completely independent. It might be that, when you plot the two, they're just completely random, which is really important and tells us something. Or it could be they're in phase or lagging. All of these things are really important things that we just don't understand now. So we're hoping that this observation will really give us a window into those temperature processes. And of course, it contexts to what we saw in James Webb, because this series of observation extends beyond what we have here through the James Webb observations and now beyond the James Webb observations. So we're really getting an understanding of the kind of the longer term variation in the ionosphere with a pinpoint measurement from James Webb on top of that. So it's really interesting.
Just, I think you referred to this earlier on, actually, and being surprised to me, but someone else on YouTube has asked, do you see Io's spot in the aurora of Jupiter in your measurements?
Yeah, well, regularly we do. In this data set, I am not seeing it in our specific scans, which tells you something. It's not necessarily something you see very often. It basically depends on the phase of Io. So as the planet rotates, the direct interactions of the localized space around Io causes the production of magnetic waves that then propagate down into the ionosphere and cause the aurora. So it's a literal pinpoint link between the planet itself and that moon, sort of a one-to-one mapping. And in fact, that was how the best magnetic field model for Jupiter had been built until Juno arrived, effectively, is that understanding of that spot and how that relates to the information. And so in this particular set of scans, no, but we have many, many observations. And in fact, 2 decades ago, those observations were the premium way to measure the magnetic field. Now we have Juno measuring, but with James Webb, we were able to see it, which is incredibly lucky, really. It's just one of those statistical anomalies that we rolled the dice and got really lucky on. The timing for the entire scan started from the base point of we want to absolutely make sure we take data at the same time as Juno's occultation. So rather than trying to get coy and line things up in a clever way by starting at the aurora and moving around to it, we set our first observation as being exactly the same time as Juno. So we were fixed in location and time from that point. And then we could have gone clockwise or anti-clockwise. In fact, in the original proposal, we just went the other way around the planet. But what Henrik figured out was if we go up instead of down from this point, we hit the main auroral, the northern aurora as it moves into view. So we were able to get lucky in that sense of being able to see the northern aurora, but we didn't consider what Io would be doing because that's a secondary concern. But as you move through, you can see that on the planet, we're up near the pole and we're positioned here. This is the Io spot here, and then you can see the main oval. In fact, what I will do is quickly scan through these, and I have a couple of slides showing that in more detail here. And so what I've done here is draw out some schematics. This is me trying to figure it out for myself. The big question was for us, we think that's the Io spot. Is that the Io spot? So the first thing we did was look where Io was. It seemed to make sense. And then the next thing I did was, you can see that Henrik's quick look has got the latitudes and longitudes built into it. So I produced a view of what the auroral locations would be for the night for the specific observation we have here. And so if you remember, we see the aurora rotate around and around, and right here it's moving into the day side. So the solid line here is the main aurora, and the dashed line here is the Io spot. And so the Io spot location, this is sort of the magnetic mapping, is here. In order for us to grab this, it's a sort of 1 in 10 or even 1 in 20 chance, basically. It has to fall exactly the right rotational place. And basically Io was just moving from quadrature into moving towards the planet, the line of view between us and the planet, but it's still very much out on the dawn side. And so this position here maps to here. And then if you map the sort of location that we're looking at here, it falls into a sort of view, sort of triangular. This is a very rough approximation. So you can see that we're just cutting through that slice, and it's very unlikely that we would actually have that Io spot fall into this along this entire dotted line. So we're really lucky. And this is a map that I made of the ionosphere using 13,000 images taken from IRTF about 2 decades ago. And you can see the main oval here. And then this is that map scaled up so that you can see all the detail. So the aurora, the Io spot is really bright here, and then there's some brightness differences in here, which you can see in this map are part of this big dark extension. So that's fun. We've got some nice views of this weird dark extension thing. We don't have names for these things yet because we're just trying to come to terms with them, basically. And then as you move to the next panel, you can see that the planet's rotated a bit, so the aurora's coming into view a bit more. And we have this nice view of the main oval and the Io spot. The Io spot's moved from here to here, so that might be really good because it's giving us a slight difference in location, so it'll have a slightly different kind of position on in the magnetic field, and we might be able to get information out from that, which would be really interesting. And then you can see a spot and a tail, which we understand. In fact, often there's more than one spot. There's a sort of second brightness here. When we've seen it with Juno, it fragments into all sorts of like small scale spots and stuff. So it's really interesting. And then you move up one more, you can just see the edge of the spot again down here, I think, which I just noticed. And then this is the main oval here, and the planet's rotated again. So now the planet's rotated even more. So the aurora is even more in view in this, and we're moving. If you step back up, we're scanning through as the planet rotates, as the triangle moves through this region into more and more aurora. And then the next step on from that, we just continue to move up along the limb and see right into the heart of it. So I mean, this is really interesting. There's a lot going on in this aurora. Looking at it, it looks a bit weird to me, and I think that there's something going on in terms of the magnetospheric interaction. Often you see more darkness along this edge, and it's brighter in the middle. But every so often that reverses, so it's reversed in this one, which tells me something's up. And then we've got lots of detail going on in here. This bump here might be a fragment and that will come out once we look at the data in more detail, but it might be a bright spot of pulsed aurora. So that could be interesting to look at. And then we've got all sorts of structure in here that will be worth looking at. Little dark fragments inside of here. Really, really interesting, fun stuff. So Io spot, yes, 3 times, which is, phenomenal. It's almost like we planned it.
Great stuff. Okay, and there's actually a question in the Q&A here, and I'm familiar with the issue, and I should probably say something about it first, but the question is, have any of the Jupiter observations ever been affected by the current fleets of LEO satellites? And again, for the benefit of the audience, LEO means low Earth orbit, and there's some concern in the astronomical community at the moment about the planned and already deployed many thousands of satellites we now have, and whether in certain cases they can interfere with observations of the sky and the objects we're looking at. And over the next decade, we might be looking at as many perhaps as 400,000 satellites and everything that follows from that. But what I, of course, can't do is answer this question, and I'm going to hand that over to Tom.
It's honestly less of a concern for us than a lot of astronomy, because while our target's really big, so it's more likely to get hit by one of these things, we're doing these long scans. And if we were to see a satellite go through this data, we've got we've got these lovely scanned images. I will go back to those. So this is our data, right, taken over a period of 2 hours. It would be the equivalent of this bright spot, basically. It would ruin 1 pixel, or maybe a few pixels. But in the broader scale of it, we would just be able to mask it out. The real problem comes not from objects like this, where you're moving quickly and on the fly. It's where you're looking at a really weak and faint object and you're integrating for a long time. And there it really is a huge concern, because our integrations are 30 seconds long. And, you know, a lot of things like distant asteroids or galaxies, you're integrating for a period of, you know, half an hour, 3 hours, and trying to get the best possible detail out. And so there's a real concern there. You can get past that by taking many more shorter integrations, but all of those are very inefficient. We use 30-second integrations and they take nearly a minute to take. For us, it's beneficial because we want the scan, we want to move around, so it makes sense. But effectively, you're halving the size of the dish. Which is not good, right? You build a 10-meter telescope, you don't want it to be the equivalent of what a 7-meter telescope. And that's what intrinsically will happen as a result of not being able to trust that you can integrate for as long as you want, because there's so much gunk out there. So for us, because of the way that we take our data, we're already doing the inefficient things that you have to do to get around the problem. It's not inefficient, it is inefficient for us, it's really annoying, but it's something we have to do because we want to move around and take data and look at the different bits of the planet all the time. So fortunately for us, it won't affect us as much, as long as it doesn't get too crazy. But yeah, it could be a problem.
Well, that's actually, and this is actually an area that, you know, and again, I'm related to this session in particular, but the RAS is doing work on and collaborating with our peers internationally. We're trying to, with mixed success, attempting to get a lid on the problem and work with the companies deploying satellites to be aware of this. For the person putting the question, they might want to look up the Earth Space Sustainability Institute, which is just been set up, which is looking at this problem too. So anyway, yeah, back to you, Tom.
Yeah, so we're doing well. You can see over on the right-hand side, the image of Jupiter. This dark band is now about more than a third of the way down the planet. It's doing that exact same scan as you can see here down at the bottom, but it's moving. It's gotten about a third of the way down. So in taking the data, it will produce something that it will go from here to about here, and we'll continue down until we get to the south. Once we're at the south, we should just about see the southern aurora coming up, which it won't be really obvious in the data necessarily until we put it into this form where you can see the two-dimensionality of the data, but that's the hope. And all of these are looking at different rotational phases. So each night the planet has rotated by a different amount, and we're seeing a different part of the ionosphere, but there is overlap that will really tell us something interesting and important about what's going on. That's giving us a broader view of the kind of ionospheric variations. You can see that there's a dark bit here and a dark bit here, maybe down here, but this is very much, we're wandering into the dark with a torch and seeing what we see at the moment in terms of Jupiter. Until about 5 years ago, we didn't really understand any variation at all. This view that you can see here, this map, really suddenly resolved for us that there's some really interesting stuff happening. So you can see down in this frame here, this is a blown out version of these observations here. So you can see the dark striations at the top of the planet here are these almost blown out bits at the top of this map over on the right here. These dark splotches are these splotches you can see, and when you take this data and you stretch it enough, there's all sorts of other stuff going on in here. There's this sinusoid down here, which is the magnetic equator. And I could definitely tell you I see that down here, but you wouldn't believe me. It is in this data, I'm convinced of it, but I tend to see things better than most people. And sometimes I'm right, and sometimes it's just me making things up. But this structure that you can see here is noisy, but it's taken from 13,000 images over the period of 5 years. So it's smooth, and so some of it's just weird noise, but anything that you do see in here is like this permanent magnetic feature. But on top of this, we do now know from some of the recent Keck stuff that we've measured that it wobbles a lot too. So if you take an instantaneous frame of this, it's going to have all sorts of weirdness that is like waves moving through the atmosphere. That's causing very small scale changes in the brightness in every instant. And so some of it's going to be instantaneously varying, like on a period of seconds or minutes, and some of it's going to be varying on days, and some of it's going to be fixed like this is over a period of 5 years. And that's a lot of complexity. And we're trying to understand that complexity. So the best way to do that is to go to James Webb and just make the problem worse for ourselves, basically. So if I go back to just looking at the James Webb, I can show you some more of the really weird and cool stuff that we've seen and trying to explain that specifically. So here we've got the aurora again. So this gives you the context again. We're looking here at the James Webb observation on the right. This little planet at the top gives you the context, and I've drawn in the magnetic context here in terms of what the aurora is doing, and then drawn on here that map that we have of the aurora and then the equatorial region, and sort of guess of the view. It's a very rough guess of where we're looking with James Webb, and it's a triangular shape because we're looking at the limb. So it's sort of, we're seeing this slice of the edge of the planet. So away from the aurora, there's no like maps of where the aurora is supposed to be, but what I've done instead is look at the angle of the magnetic field. So either you're at the magnetic equator. So basically, if you think about on Earth, if you've got a compass, we're used to the idea of a compass pointing north, right? And when we say that the compass is pointing north, we think of it as pointing towards the rotational pole of the planet. It's not doing that. It's pointing towards the magnetic pole of the planet, but it's not even doing that. It's pointing in the direction of the field line that you're standing in. So if you go to the magnetic pole of Earth and you have a compass, the compass doesn't want to point in any direction. It wants to point down. And so that angle is really pointing down rather than in a direction. So at the pole of the planet, it's either pointing up out of the planet or down from the planet. And then when you're at the equator, it's pointing perfectly parallel with the Earth. And then it sort of goes from parallel to perpendicular at the poles. And so one way we can measure the magnetic field is that angle, whether it's parallel or perpendicular. And so what you can see here is a plot of that parallel to perpendicularness. And you can see that down here at the bottom, it's very significant. It's minus 79. And this is very weird, and it's Jupiter being weird, basically. So at Earth, it's almost like a bar magnet. There's some variations on top, but basically if you hold a bar magnet and you sprinkle your iron filings around, all the iron filings line up with the magnetic field. It's a classic experiment, right? So the fields go into the top and the bottom and then are parallel. But Jupiter has this weird blotchy middle bit where it starts behaving really badly if you want it to be like a bar magnet. It's actually almost like a big bar magnet with a little bar magnet at a weird angle. And that was described by some people rather controversially maybe 15 years ago, and based on some of the trying to explain why the aurora is this weird misshapen shape. And what Juno has done is actually confirm that that's true. There's something causing a weird anomaly in the subsurface of Jupiter, maybe 1/10 of the way down, that's causing this really weird kink. And so the magnetic fields in the equatorial region are really weird. And that's like, we think, where a lot of this weird structure comes from in the ionosphere that we're looking at. And so what you can see is here, we're switching from red to blue. And that switch from red to blue is the magnetic equator. It's this perfect equatorial region. And you can see this dark ribbon running through our data from 20 years ago. And that shows that the magnetic equator is dark. We don't know why. I have no clue. There's 100 theories now about why that is. So we really want more data to try and test that, right? Because it could be anything. It could be that it's hotter or colder. It could be that it's being eaten away. It could be that we're removing the H3 plus or pushing the H3 plus up or down. Who knows? We need more data. So James Webb is the perfect thing to do more data with, because it's not this really coarse map. It's incredibly detailed. And we happen to get this cut that goes right through this equator region. And you can see it's just really dark at the top. There's almost no ionosphere at all at the top. And then everything else is much brighter. This slides through this equator bit here. And it perfectly matches up with where the magnetic field is perfectly parallel. It's very weird, but we see something similar at Earth. There's a lot of discussion about whether it is the same at Earth or not. But basically at the Earth, when you go perfectly parallel, the atmosphere blows through that, and it basically creates a fountain of ions that shoot up into the sky and settle down either side. And so at Earth, there's a really good explanation for why you get less ions in that central region, but that doesn't necessarily work for Jupiter. And there's a lot of discussion about that. So we're hoping that some of these observations will help with that. But that's this really nice darkening here, hugely darker as a result of that one feature. And then you can see there's all this other weird stuff going on down here, which causes, we think, a nice dark spot here. This is work that my student Katie Knowles is really working on now. So, again, no clue why that is. But for some reason, when Jupiter goes almost vertical, the ionosphere disappears. It's something you don't even see at Earth. It just never happens at Earth, because the only place where the magnetic field goes vertical at Earth is at the poles, where there's aurora. So the aurora completely destroys any hope of seeing that. Here, there's no aurora, or it could be aurora, it could be dark aurora, I don't know. But it's really interesting. And so the planet's going to rotate. We're going to move down from here, down a slice. The planet's going to rotate, and this feature is going to go onto the limb of the planet. And that's what happens here, right? So this big magnetic anomaly in the south is right on the limb. You can see that there's a sort of spike here and a spike here at the bottom. So it's particularly vertical in these two places and not in the middle. And it's dark at the top, dark at the bottom, and a spike in between. It's really cool. So this is something that Katie sort of has used this map and a lot of looking to sort of go, oh, maybe that shape itself is doing it. But mostly it's just this dark blotch. Well, what this seems to be saying is that, no, it's really specific. It's really tight. Just where you see these two really, really tightly, and where the magnetic field is coming straight out of the planet, it's getting dark. And anywhere around that is not getting dark, which is just really cool if it's right. This is really preliminary stuff, but Katie will be looking at this and with the rest of us and trying to understand that more. But as I said earlier, we've got this weird circle of darkness here surrounded by what looks like a halo of bright. There's nothing in the magnetic field that would suggest anything. But this magnetic field is taken from Juno data from 33 orbits. So it's gone around the planet 33 times. So it's only got 33 slices through 360 degrees of the planet. So its actual spatial resolution is on the scale of this image in terms of the magnetic field. So on the limb and maybe right on the edge of the image of the two slices that it's had with its magnetometer close to the planet. Whereas here we're seeing incredibly tight detail. So we don't know what's causing this, but it might be caused by the magnetic fields. And if it is, then that might be giving us an incredible window into really, really fine scale magnetic structure. Or we go back, we take another image, and this dot just disappears and it's not there anymore, because this is actually like something welling up or something spewing down from the magnetosphere at that moment. And, you know, so there's a lot of things to try and think about. And again, that might be a reason to go back with James Webb in the future. We might make the case that if we look at these specific locations again, we can again see what we're seeing, and do we see the same magnetic anomalies or not? So there's reasons that we want to return with James Webb again in the future to try and pull these things out. Oh, so there is some really exciting stuff in this. I mean, you know, this is the first frame again where we see this darkening, but you can see, you can draw lines of dark all the way around this. It maybe looks like, I mean, you know, people who've looked at those supercell structures of the sun, almost like blotches of high and low. And we've seen this before only in James Webb. So Henrik's been able to see that in James Webb before, but obviously different location and different appearance. Didn't look anything like this. We're just starting to understand any of this, but it's thrilling stuff. I mean, I've just described about 5 papers that we may or may not write, depending on how things go. It's just really amazing, and that's 2 or 3 frames that I pulled out. There are more than 30 frames already. We've got another 5 to take. So just really, really interesting stuff, basically.
So, Tom, I was wondering, actually, I mean, obviously, you know, some of these things like the aurora have that direct connection to the sun as well. Can you tell us a bit about that overall interaction? You know, I mean, we know that the Earth is obviously the northern lights and so on. I think most people are aware that there's that connection.
Yes.
Activity on Jupiter. Are we seeing the same thing?
It's difficult. So let's talk about the Earth, because the Earth is easy. I say that knowing that there are hundreds of researchers working on understanding the link between the sun and the Earth. It's a very active field. There's a lot of disagreements about how that process works. So it's a sort of flippant thing to say that it's easy at Earth. We also have 80 to 100 satellites measuring things around the Earth simultaneously, as well as a whole slew of ground-based observations looking at the aurora. And, you know, it's this incredible level of detail that we have for the Earth to understand it, and we still don't understand it, which is always something that contextually we have to remember when we look at data from Jupiter, because Jupiter is probably much more complicated than the Earth, and yet Earth is a struggle to understand, so it's always a bit fun. For Earth, what we do know is that Earth has a magnetic field generated in its liquid iron core, and that magnetic field passes through the planet and out into space. If Earth was the only object in the universe, would be very lonely, but also that magnetic field would continue on into infinity. But the sun also has a magnetic field that's very strong, and that magnetic field gets trapped in the stuff called the solar wind, which is a stream of ions and electrons streaming away from the sun, and traps that magnetic field as it washes outwards, and that moves out very, very far from the sun, but ultimately meets a heliopause, and then the surrounding galactic space has a magnetic field. So Voyager is passing through that layer boundary now. So, but Earth sits well inside of that. So there's a region when you're at a distance from Earth where you just see the solar wind and the magnetic field of the solar wind and the sun. And then when you're really close to the Earth, like we are on the surface, you just see the magnetic field of the Earth. And then there's a boundary between those two, where there's an interaction between the magnetic field of the sun and Earth, and they can connect and reconnect with each other, depending on the complex physics of that environment. And so when that happens, you can have the funneling of energy from the sun and the solar wind into the sort of outer extremes of the magnetosphere of Earth, this cavity that the Earth has embedded inside the solar wind. Basically, the Earth's magnetic field shields us from that solar wind, but there's links along the edges and boundaries of it that ultimately push things around inside of the Earth's cavity, and that process is what drives the aurora. The streaming of energy between the solar wind and the Earth's magnetic field then cascades down along the field lines into the Earth's upper atmosphere. And fortunate for us, the top of the atmosphere has ions and electrons that can carry that current. And so you generate currents in the magnetosphere. They close in the top layer of the atmosphere, and it creates a circuit just like a light bulb, basically. You have energy moving around that system, and that energy, just like an old school television, fires electrons into the atmosphere and makes it glow. And that's how you make an aurora at Earth. It's not that simple at Jupiter, and it is honest to say that we just don't understand it. I can say that because I'm one of the people trying to understand it. Until 4 years ago, we thought we had a really good picture of what's happening, which is that Jupiter has this volcanic moon Io, and Io is generating all of this plasma. And so unlike the Earth, where it's this empty cavity, the space surrounding Jupiter is actually filled with plasma. And all of those ions are trapped by the magnetic field. So they have to keep rotating with the planet. But they start drifting away from the planet. And so the Keplerian orbit of those individual molecules, it gets slower and slower, just like the planet's orbit slower and slower as you get away from the sun. And so that's a problem, right? Because the Newtonian physics wants them to move slowly, but the Maxwellian physics wants them to move with the magnetic field. And so ultimately something breaks. You can't provide enough energy to the ions to make them rotate with the magnetic field of the planet if they drift so far away that the Newtonian velocity of the orbit makes them move very differently. And so ultimately that ion starts moving towards its Newtonian Keplerian, the Keplerian orbit. So it's moving through a magnetic field and it generates a current. And so that breakdown in co-rotation, as that disk of plasma surrounding the planet starts moving away from the motion of the magnetic fields, drives this huge current into the planet and generates this really bright continuous aurora. And it's why we can see the aurora at Jupiter no matter what. It's always there. It's really bright. That's the story from 5 years ago. Then Juno arrived at Jupiter, and everything that it started showing us confused that picture and made us really confused about what the hell's going on at Jupiter. And we're just starting to pick up the pieces of that confusion now, basically. One thing is that some of the aurora is made by that process, and some of it's made by just the interactions of all that plasma causing waves in the magnetosphere, and those waves start dumping energy into the particles in that region, and that causes an acceleration. So that's called wave-particle interaction. You do see that at Earth too, but it seems to be really dominant at Jupiter in some ways, but only in some circumstances. Another is that we talk about this breakdown in co-rotation as being dominant, but actually there's Earth-like currents as well. Just like the Earth's aurora gets generated by this interaction with the solar wind, that does seem to have a really important effect. So another of my students, Royan Wang, is currently looking at minor revisions on a paper that really helps explain that process. And it's complicated, basically. The ionosphere is not acting as a single thing. It's more, as we know, as we see in the James Webb observations, is this multiple layered region of the top of the atmosphere, and the physics in that layer changes as you change altitude, basically. And so it's all very complicated interactions are causing all sorts of tension in there. So then you look at those UV observations of Jupiter, really short timescales with Hubble, and you see these incredible like bursts of brightness, and those bursts of brightness seem to go all over the place. So we have all these different regions that we've named that we think link to vastly different bits of space. And when you look at them on the long time scale, they have very different characteristics, and they clearly map to different bits of the magnetosphere. And then there's really short timescale stuff just shows aurora going all over it, which doesn't make any physical sense at all. It breaks your brain when you think about it. And my interpretation of that is that there's another source of aurora, which is more like the sun. So when you look at solar flares, You see these weird wiggles called ribbon flares on the sun, which look very reminiscent to what we see in the auroral region of Jupiter, but superimposed on top of a bright aurora that's already there. And so there's 3, 4, 5, 6 sources of aurora at Jupiter, all scattered in amongst each other, all causing kind of different effects at different timescales. So it's really complicated. A lot of what I've told you is just me making things up in my head to try and explain it, and trying to basically square the circle of none of this data making any sense at all. But Juno has basically ruined our understanding of Jupiter. But that's great, because what that means is we had it wrong, and now it's broken things enough that hopefully, with time and enough researchers understanding it, it will start solidifying into what is actually happening, rather than this poor interpretation that we used to have.
Okay, thank you for that. Well, there's one question which I suppose sort of relates to this. And it says, just as the Earth has a region referred to as the South Atlantic magnetic anomaly, where the weakened magnetic field has a significant effect on the radiation flux in space above this region, could similar greater anomalies in Jupiter with greater magnitudes be causing the ionospheric darker areas observed?
Yeah, definitely. So again, I think it's confused and complex. This is specifically the work that my student Katie Knowles has been doing in the run-up to these observations. And she's been looking at the magnetic field in lots of different ways. So you can look at the total power of the magnetic field at the surface, or the power of just the component moving in and out of the planet, or this dip angle that I showed here. And all of those have different effects. They will have a different effect on the kind of brightness. So when you look down in this map here, there is a bright region on the left-hand side. That is a region where the field is weak. And then over here, it's dark, and that's a region where the field is strong. So that might be a one-to-one analogy to what you see in the Southern Atlantic anomaly. The anomaly is bigger here. If you look at the total percentage of magnetic field strength, the anomalies you see at Jupiter are significantly larger. But that only explains some of the stuff. And Katie's been showing that we haven't actually written up or published it, is that other things have an effect too. So the dip angle has definitely got an effect, which is not anomalous to the Southern anomaly at all. And then there are regions where none of the magnetic fields align with brightness changes. So this dark feature over on the left-hand side of the map, here underneath another feature, this styration, we have no clue at all. We have nothing. None of the magnetic field changes map to that at all. Yet it's solid over a period of 5 years. So it can't be anything other than something to do with the magnetic field, because when you look at clouds in the lower atmosphere, if you've ever seen some of like the Cassini approach to Jupiter or anything, the atmosphere is twisting and bending. When you look at more than a day, you see all of the weather features changing really dramatically, and they're all moving independent of the interior of the planet. And this is over 5 years, so all of those would just smooth out into nothing. The Great Red Spot moves with time. So at the time of these observations, the Great Red Spot was about half the planet away from where it is now. It was completely the opposite side of the planet compared to the magnetic field, and it's moving the whole time. For anything to show up in this map, it has to be fixed over 5 years, which is none of the lower atmosphere at all. So it has to be something to do with the magnetosphere in some way. It could be that there's a jet of cold air moving through consistently compared to where the aurora is, and that's causing it to be darker or something like that. We don't know, but there's definitely features that really tie in with the Southern anomaly. One thing that's really interesting is some of the researchers into the magnetic field feel like that magnetic field region is changing. This sort of complex region in the equatorial region, they think, is moving with time. And that is very comparable to the Southern Atlantic anomaly. I think a lot of people know that the pole of the planet moves. Over the last 40, 50 years, we've seen the magnetic North Pole drift from sort of mid-Alaska up towards the magnetic pole. But actually, the stuff in the equator moves more dramatically than that. That bulge, that shape has moved. In fact, it's called the Mid-Atlantic Anomaly, and it isn't even in the Atlantic anymore. It's over Brazil now. So that's how much it's moved. And so that would tie in, because it's those equatorial regions that are much more dramatically changing, both at Earth and Jupiter. It's just that at Jupiter, they're vastly more pronounced. It's much bigger anomaly.
Thank you, Tom. I'm just wondering if we should rejoin Henrik and Paula briefly, see how they're getting on.
Yeah, that makes sense.
Yeah, certainly. Yeah, we're doing really well. We crossed the equator, moving down towards the southern aurora. And I think this data is looking great.
You can see that in the window on the right here. And in fact, I will zoom in onto just that window, I think, so we have a better view of the imager. There we go. So this is the instrument as Henrik is seeing it from Leicester, and as you would see it if you were in the control room in Maunakea as well. It's really funny, but you basically do remote observing from the summit as well. It's exactly the same setup. So you log into your own computer. You're on the computer that runs it, and you're logging in as if you're remotely observing from the summit. But you see something like this, and this panel is showing you the ongoing images being taken over here, and this lightly colored green box is the guide camera guiding on the south, and you can see it down here zoomed in, looking at that southern pole and keeping the observations in place. And then basically over time we're moving that box upwards, so slowly but surely the box moves upwards, and in moving upwards it moves the planet upwards, and the slit is fixed, so the slit moves down over the planet basically. So that's how we build up a scan like we saw of the planet from one pole to another, and we're more than halfway through right now.
How long, Henrik, Paula, how long does it take you to get your raw data into something you can use and analyze?
Well, Tom showed those preview plots of the past IRTF observations. That's relatively straightforward because I got some code that I wrote to do it. But that's just a preview plot. To do the full analysis, it's going to take a bit more thinking about. I think we have all the tools in place. It's just a lot of data. And same with the James Webb data we got. It's just,
yeah.
In one sense, it's really familiar data to us. In another, it's not, because it's James Webb. So things are a little bit different and better. You know, I remember looking at data from the Great Red Spot, so the ionosphere above the Great Red Spot. I was like really confused looking at the data initially, like, what? This spectrum looks like a computer model. There's no noise in this data, which is unheard of using ground-based telescopes. There's always noise in the data. It's just beautiful, beautiful data. So that's quite a luxury, right? Using the best telescope in the world to do science with. That said, I don't want to knock IRTF either. IRTF is an amazing facility and has allowed us to have this month to observe Jupiter every other day, which is really unusual. We've not had anything like this before either. So different telescopes for different science projects, I'd say.
And yeah, it would be a bit of a challenge to get a month of time on James Webb, I imagine. Yeah.
Yeah. I don't know. Some of those, when people observe the first galaxies and things like that, you do need a lot of time to stare at one single bit of what looks like empty space for a very long time. So I don't know. That's a good question. What is the longest web program?
That's a fair point, but I'm sure we can find out, or something. Maybe someone watching can understand.
The longest class of program is above 80 hours. So just on, I think, about a quarter of the time that James Webb is observing, it's on a program that is more than 80 hours long.
Out of interest, I mean, you generally assume with some of these flagship projects that there are many tens of collaborators on them. And is that true for the work you're doing as well, or for this JWST time you've got?
No, it's not. For James Webb, there was certainly a broader set of collaborations than we would normally have, because the kind of science that you can get out from these observations is so mixed and profound. So that, we're interested in the top bit, but you go to a different wavelength bin, and suddenly you're looking at the stratosphere, not the ionosphere. So we have collaborators that work on the stratospheric science, and there's some really interesting and intriguing possibilities there. There was an impact quite recently that some of the viewers might have heard about. Some Japanese and Chinese observers saw an impact into Jupiter about 8-10 days ago. So there's the possibility that I hadn't even considered, because I don't think about these things, but given how good a super sniffer the James Webb is, that it might be able to see chemistry differences from that specific latitude, for instance. There's a new chance thing that might be really amazing. And then there's the lower atmosphere, what's going on in there? What about the thermal stuff? Is there stuff in the thermal data that's giving us something new and there's all sorts of really wonderful things that could come out from this that we just haven't thought about. So naturally, we were rushed and we didn't have enough time to think about things as much as we would hope. But because both Henrik and I were involved in the program of early release science, and we were both on this proposal to look at the Great Red Spot and the auroral region, that was already an in-place collaboration that covered a huge range of people. So we included some of our colleagues from that PI that sort of bracketed those different science areas, and so we had, I think, maybe 10 co-authors on our proposal, but it's not the same scale as many of these things are. And similarly, we have about that many on a lot of our proposals, but that's because we're keen to include all of our PhD students. And in fact, wherever possible, we have our PhD students lead the proposals, because it turns out PhD students are much more keen and eager and write much more exciting proposals than boring old farts like me. And so the proposal that we put in here was one that I had put in a much more poorly written state, apparently, 2 times, and we never got the time. And I handed it over to Katie, and she got the time with her much better written proposal. And then similarly, Henrik was talking about some Uranus observations on Keck. That's another of my students, Emma Thomas, who's been doing a lot of the Uranus observation and has just we received news this week that her first paper on Uranus has been published, which is the first detection of an infrared aurora at Uranus, which is really cool. Yeah, so it's really important to involve the early career people, obviously, but then you can either do that by having them write it, but you have to make sure that they're on the proposals as much as possible. So that means we have tens, as in 10 people, but we're quite a tight-knit community. Luke Moore over in Boston, Henrik in Leicester, James O'Donoghue's in Japan until October, and then coming back to the University of Reading. And we invite other people to work with us often as well, depending on the specific science that we're looking at. We're quite tight knit especially compared to galactic redshift communities, where it's hundreds, and exoplanet communities where it's hundreds of people often trying to do the same thing, often quite competitively.
We have a I should say, actually, as a short plug, our supermassive podcast is covering Uranus in a couple of weeks' time. I'm not sure about the interview list, the guest list, but we've done Jupiter and Saturn II not long ago as well. So there's definitely a public appetite for this. I was going to ask one question. One of the things earlier on, I mean, I think when you were comparing Jupiter and the Earth, you talked about the fact that there are obviously no remotely comparable places from the human perspective. I think I remember very frequently reading about the very high levels of radiation in the Jovian system as well. Because I know there's obviously that interest in Europa, particularly, and some of the other moons as potential habitats for life. Can you give us a feel for the kind of radiation levels we're talking about?
They're fairly insane levels of radiation. Jupiter especially. Jupiter's particularly hard. to the point where most of Juno is inside this giant metal box, basically to try and protect the instrumentation. So it's really hard to get a handle on the Van Allen belts even, right? And around Earth, there is a radiation environment. And before we went to space, there was models of that suggested it could be possible that you would cook all of the astronomers if you sent them, all of the astronauts if you sent them through that layer. There was a real concern that the radiation environment was so horrific that the metal of a spaceship would not protect them. It's still not great. There's very few astronauts that have been through that region. Everyone that is currently in space is well inside of the Van Allen belts. They're very close to the surface of the Earth comparatively, and it's a magnetic field trap. Basically, it's not the atmosphere of the Earth at all. It's the magnetic field strength traps them in that specific region, and they're very energetic and they bounce between the poles. The magnetic field of the Earth is much stronger towards the equator, where currently most astronauts are, and so it's much more shielded. But it's when you go to the moon that's more problematic. So, in fact, it's traveling out to the moon and back that we've encountered that radiation environment. And you hear from astronauts that went through that process that they would see bright spots flashing when they closed their eyes, and that's those incredibly energetic particles flying through their eyelids and hitting their retina, which is a bit scary. But compared to Jupiter, it's nothing. It's a very, very weak radiation environment. It's very much more dangerous, especially in certain regions. It's effectively defined the Juno orbit. The Juno orbit flies over the pole and down very close to the planet and out again in a way that avoids that radiation environment. And it's now tilting as we go on into more and more dangerous regions, because it's worth the risk now, because the science that you can get out is worth risking being irradiated by those powerful impactors. But you see the radiation painted on the surfaces of the moons. So many of the moons have a different color on one side than the other as a result of being irradiated by that radiation. And it's very likely that any life that would be able to survive the harsh environments on the surfaces of these moons would then be destroyed by the impact of this radiation. So there's real hope that there is life on the moons of Jupiter, but it has to be under the surface, because there's no way that environment, it's unlikely that unless never say never, but it's unlikely that environment would be survivable by life.
So I've got another question here, which is, since the plasma generated from Io is likely from the more volatile volcanic gas components it emits, such as sulfur and its oxides, how does this, if any, affect the Jupiter auroras in comparison with the Earth's auroras generated from the solar wind comprised of ionized hydrogen, protons, and electrons? You want to take that one, Tom?
Yeah, sure. So it does have something of an effect. What I would say is that when you generate an aurora, it's not so much the impactor that changes what you see as the thing that you're impacting into. So the auroral colors at Jupiter are very different from Earth. Earth is green because there's an oxygen line that's very readily accessible. Similarly, you see that same aurora at Europa, for instance, because the water gets split apart into hydrogen and oxygen, and that oxygen gets radiated. So you see exactly the same color aurora at Europa as you do at the Earth because of that oxygen line. And there's a bit of nitrogen too, so you see some reds. At Jupiter, it's primarily hydrogen, and so you see some pinks and purples in the visible. And then in the infrared, it's the H3 plus that we're looking at. One place where it does have a very dramatic difference is in X-ray aurora. X-rays are really high energy, and what you're seeing there is photons coming from the infalling particle as it gets super accelerated into the planet. So it's not the atmosphere that's producing that aurora, it's the actual stuff as it flies in. Bits of the electrons get streamed off and stuff. Photons incredibly high energy. So there you do see very different strong differences. You see a lot more sulfur and oxygen and carbon emission lines, although some of those are contained in the sun as well. So it's not dramatically different necessarily. There is potentially some effects in the fact that those are much heavier and are more affected by the Keplerian drag forces than hydrogen might be. And so there are potential differences there, but it has a very strong effect on what you see at Io. So Io has a sulfur aurora rather than an oxygen aurora because the sulfur in situ. And potentially has a real effect in terms of what we're looking at. These weird striations might be caused by the fact that that material is forced down into the atmosphere. And as I said earlier, H3+ is incredibly reactive. So at Saturn, we see very stark brightness differences because the water rings are streaming particles at certain magnetic latitudes. So you see bands of darkening and brightening, and then right at the equator, it gets completely swamped just because all of the neutral water is falling in from the rings into the atmosphere. So the H3+ is dramatically changed, and the ionosphere itself is dramatically changed by that at Saturn. We don't know the extent to which that happens at Jupiter, but it's very possible some of the brightness differences that we see in the atmosphere are directly resultant from that same process of sulfur and oxygen from Io streaming in and then recombining with H3+ and becoming some other species that then is lost to us and thus darkens that bit of the ionosphere. Is part of what we're trying to understand, and the spectra will certainly help us. The James Webb spectrum will help us give more understanding to that process if we've captured those dark bands.
And I've got another one I'll take partly as well, which is from Anne Hilton, who's watching on YouTube, and she just asked when Jupiter was first seen. And then there's some discussion. We've put things in the chat about how, well, it's so bright as a planet that if you have a clear sky and human beings looking up at the sky, it's impossible to believe they didn't notice it. But the other question that might follow on from that is when it was first seen with a telescope, or seen through a telescope, I should say. And that was back in 1610, and it was Galileo Galilei and another astronomer, Simon Marius, were two of the first people. I think one of the features of the early history of the telescope is people pointed them at almost everything in the sky. So very quickly people saw what planets were like. But if you've ever looked at it with, say, a pair of binoculars, it's not a very different view to the one Galileo would have had, and you'd have seen a little small oblate sphere. Basically, it looks like an ellipse, a sort of flattened circle shape, because it rotates so quickly. And they would have probably seen that, and also the four largest moons. So, but I think what's remarkable, obviously, is that you go from that and what you can see with your eye, just this bright dot that moves across the sky against the stars much further away, to what we can do now with telescopes like the one we're actually using at this moment.
Yeah, it's a profound change, isn't it? But those early observations, the wobbly little sub-cylinders, were vastly more powerful in terms of the change that they enacted to science than anything that we could do.
You're not expecting to overturn the world view of the
I certainly hope not.
Well, you never know. Yeah, I mean,
Sure, right?
I should say, yeah, that this is. So, Anne, your question is, when I think about the impact of it, what Tom's describing, you move from a worldview where everything was thought to be going around the Earth. I mean, that was still being contested at the time, even before that, to a demonstration that some objects, namely the moons of Jupiter, move around Jupiter. So not around the Earth. And that was the inherently controversial observation that got Galileo into such trouble with the then Catholic Church and all the history that followed, and certainly helped cement that heliocentric view of the solar system, the idea that it was the sun that dominated the solar system rather than the Earth.
Yeah, that, and looking at the moon and seeing that it's not a perfect sphere, a god, it is just a bunch of mountains. It was also profoundly shaking to a lot of the establishment, the idea of sort of Aristotelian view of this perfect heavens, that everything is perfectly spherical and everything moves in perfect circular orbits around the Earth, or even around the sun. You know, it's the idea that Jupiter is its own center to the moons just, shook the very foundation of society, basically.
Do you happen to know how many moons we now think Jupiter has? I lose track of the number, Tom, but it's...
I don't know. I think some have been detected quite recently. It's in the range of 50 or so, I believe. But yeah, Juno is less interested in looking for that kind of thing than Cassini was. And so the count for Saturn is probably higher, I would guess, still, just because there was specific dedication to looking for small irregular moons around Saturn by Cassini, whereas Juno is much more focused on the planet itself than the moons, although there obviously are some really nice moon observations. But, Jupiter is closer. So ground-based astronomy has been catching up because of the sensitivity that we can achieve now. So
I'm gonna put this as a kind of astronomy pub quiz question to Henrik and Paula to see if they know how many moons Jupiter has. I'd have to look it up, I have to say. I thought it was even higher, actually.
What's been said before? I think it's 95.
That's pretty high. Yeah.
Yeah.
So does it? Sorry, Paula, go ahead.
We were Googling it.
That's fair.
We were doing the last observation before this one, because there's still a debate between 80 and 95. So we wanted the exact number, but yeah, it's predicted 95, but yeah.
So we don't even know how many moons there are.
But then, because I think it's still like debated what classifies as a moon and what not, because some could be just captured asteroids and then so on. So I don't know.
Yeah, it's fairly likely we've found all of the moons that formed around Jupiter. There's an awful lot of irregular satellites that orbit retrograde or in scattered orbits, which are undoubtedly captured. And then it's a resolution issue, right? Because there's the great possibility you could have millions of moons around the Earth if you go too small. Because if you go down to dust sizes, then the Earth has lots of moons. It's just how big is a moon? It's an interesting question.
Right. And I think my favorite space fact, talking about the moons of Jupiter, Jupiter's largest moon is called Ganymede, right? And Ganymede is larger than Mercury. So, is Mercury even a planet?
I don't think, do we want to start that debate about what is or isn't a planet again? I remember it very well with Pluto.
Well, one really interesting aspect of that is Triton, because pretty much all the other large moons around planets are definitely moons, in the sense that the way they orbit tell us that they formed around that planet. But Triton is the large moon around Neptune, which is unusual because Uranus doesn't have a large moon like that, like a super large moon. It has pretty decently sized moons, large enough to circularize their shape, but Triton's really big. It's only slightly smaller than the really big moons around Jupiter and Saturn. But it's retrograde in its orbit. It definitely didn't form around Neptune. It was definitely captured at some point. So is it a dwarf planet or a moon? Is a really interesting question, because in terms of formation history, it's not a moon. It's a dwarf planet. But it's a moon because it orbits the planet. So ultimately, these are semantic questions that come down to what is it that we're trying to capture, and ultimately it doesn't really matter. But Triton's in a wonderfully weird and wonderful world that has all sorts of interesting chemistry and physics, that align it more with Pluto than Callisto, for instance. So it is interesting to think about.
Do you a couple of things come to mind as you want. Firstly, we've got somebody commenting, they've quoted from, I guess it must be from a news story, saying that the IAU had recognized 92 moons for Jupiter in February. And that number might have gone up. It probably depends on exactly what you're describing about the definition. And then I was thinking about the distinction between moons and planets, not just in terms of where they are in space, but actually the characteristics, because I guess, Mercury's barren. Our moon is barren. They in many senses they have more in common than whereas on the other hand, looking at say Triton or Titan or Io or Europa or all those moons, they have the activity that is more reminiscent of a planet. They're not static. They're not static barren objects that are just covered in craters.
Yeah, and the honest answer is that we just don't care about what they're called. I am a big advocate for, and I have been on proposed space missions to Triton because it's a really interesting place. Is it more or less interesting than Pluto? Comes down to a discussion about what happens there. What's the physics? What's the processes? It's not because one is a moon and one is a dwarf planet. And Pluto doesn't become intrinsically less interesting because it's not a planet anymore. It's still a really interesting world that has really interesting processes. Those processes are different from Triton for very interesting reasons. One thing I would say is that for our science, intrinsically, it kind of is more interesting because Triton sits inside and outside of the magnetosphere of Neptune. And so there's interactions that happen that are really interesting to our science, whereas Pluto is out in the solar wind constantly without those interactions. So there are reasons why moons are more interesting for certain subsets of science, but that doesn't necessarily transmit more widely. If you're a geologist, they're both really interesting for different reasons. A moon might be more interesting in association with that, though, because of the tidal forces. So Triton, we don't know whether Triton has weird water geysers because of a greenhouse effect on the subsurface or because it has tidal heating around Neptune. That's one of the reasons why we want to go back to try and understand that. But it's very likely that if you put Pluto around Neptune, it would have similar interesting thermal heating. So moons do have some glitter put on them to make them shinier as a result of orbiting around planets, even if it's just because those planets make them do stuff that they wouldn't do if they were out in space.
So I was just another thing thinking back towards the subject what we were discussing today, the observations, is you've obviously studied aurorae on Jupiter and Saturn and now Uranus. Do you detect them on Neptune as well?
Well, that's an interesting question that may or may not be answered in the next year. What I will say is that Henrik is the world expert on not detecting the aurora of Neptune. Over the period of the last decade or so, our team, led by Henrik, have tried to find the infrared aurora. We have colleagues that have tried to find it in the UV. There, it's basically impossible. Everything that we knew from Uranus was that it should be nice and bright, at least to see the ionosphere, if not the aurora. We now can say that we've seen the aurora of Uranus, but that sits on top of a nice glowing disk, sort of this disk of glow that you see at Jupiter as being 100 times weaker is actually brighter than the aurora at Uranus. At Neptune, though, Henrik can describe the days of observations where we've tried to find stuff.
Yeah, I spent 15 hours observing over 3 nights at the IRTF, just staring at Neptune, staring. I was co-adding the data, I was going along, and it was so exciting. I'm going to see it for the first time. Just saw absolutely nothing. It's the first and only time I've written the paper before leaving the mountain. Easiest paper to write.
A search for that didn't find. Yeah,
exactly. Yeah.
Did you? Are you expecting, say, JWST to be able to help answer that then?
That's certainly our best chance. Yeah, for sure. You really need that sensitivity that James Webb has to be able to do it.
Yeah. I have some other ideas about how we could do it. When you look at Uranus, sometimes the aurora at Uranus gets really bright. So it's normally dim and we can see it dimmer, but sometimes it just gets really, really bright. And our calculations suggest if that happened at Neptune, we should have seen it. So telescopes, everyone observing loves days like this when the weather's beautiful, but there's days when the weather's pretty grotty. And so there's a possibility of us asking for time when it's grotty, which means you get loads of time, right? Every year there's time when no one can do any observations. And so if you have observations you can do, they love that. And so I always had this idea that we could ask someone like VLT to, whenever it's rubbish weather, to look at Neptune and not see anything, but maybe see something. So that's my one get out of jail free card if all else fails. But if there's anything in the world in our astronomical community that could see it, it would be James Webb, I think. Certainly, I talked to Tom Jabal about this years ago, although I talked to him recently about this and he said, no, that was definitely you that said it, but it wasn't me, it was Tom Jabal that said this. He said, oh, we'll see it in seconds. So he believed, long before James Webb was launched, he believed that were we to point it at Neptune, we would see H3 plus very quickly. But having talked to him recently, he told me that wasn't true, that it was definitely me that said it. So the memories of humans is clearly much more fallible than telescopes.
Yeah. So anyway, Henrik, Paula, how are we doing with the observations in Hawaii at the moment?
Yeah, really good, I think. We have exactly 10 minutes left. We've reached the south and we started moving back up north just to get a little bit more data. And then we'll basically close up the instrument and yeah, that's us done.
So are you what time of day is in Hawaii, or what time of night rather? I'm not sure actually. Night, obviously, but
yeah, it's
3:30 in the morning.
3:30 in the morning, yeah.
So sometime till sunrise. So presumably someone will be using the telescope after you then, or
Yes. Yeah.
project. Are you yeah, okay. So it's gone on, but you I mean, out of interest, I mean, you're obviously talking to an operator there, but this isn't then, you're not just putting in code and getting the telescope to do a scan and then going back up. You're intervening at different points as well, or?
Oh yeah, yeah. We're controlling the guiding, so where the telescope is pointing. That's the panels with the image of Jupiter on them. We're also controlling the spectrograph where we're taking the actual data. So this is quite a hands-on telescope. The telescope operator mainly deals with large movements of the telescope, like going from a star to Jupiter and things like that. And we do all the small detail stuff, which I actually kind of like. It's kind of fun to be so in charge of the telescope. It's, James Webb doesn't work like that at all, of course. You fill in this form, well, it's a very complicated form, but you say, we want observation of Jupiter, it's going to point here, it's going to be executed at this time, all these different parameters and things like that. So very different processes. You do get telescopes that have automated systems. So you basically design the observations before they happen. And then the observer is not at the telescope to do their observations. It's done by staff at the observatory. The very large telescope is like this. So they basically load your program in and press go, and the telescope will execute your program.
There.
Except, of course, ours are horribly difficult, and so they refuse to do that. So
Yeah.
unfortunately, when we do observations on the VLT, we have to fly to Chile to do them because they're just too difficult. It's a real shame that they can't do them as the program. It's really, really unfortunate. Yeah, I think you guys are just going to point out what I had just spotted.
Yeah, that's right.
Go for it, Paula. What were you going to say?
That there's the great red spot just on the left side.
Oh, great. Oh, is that just turning into view then?
Yeah. I think it's a bit too late maybe to jump straight there because we won't have time in the observation maybe, but I don't know. Maybe I'm wrong.
And that just was it there at the start? I mean, I was just thinking Jupiter no, of course not, but Jupiter rotates what, every 10 hours or something?
That's right.
Yeah. So it would have been behind the planet all this time.
Yeah.
Outside.
But Saturday we managed to jump right there when it was in view.
So there's another question here, which is from somebody who's been asking, it's just AEC asking lots of questions actually, but one here is, was the now retired Sophia flying telescope, as in telescope on a plane rather than telescope that just flies, used to make any infrared observations of Jupiter? I have no idea. So
I think of Jupiter, yes. We always dreamed of using it. In fact, we had an observing proposal accepted as a team to observe the year it was cancelled. So had it not been cancelled, we would have been able to use it. It's a really interesting idea, sticking a telescope on a jet plane and flying the plane as high as you can so you get past a lot of the atmosphere. It's sort of a cheap version of a James Webb Space Telescope. But the advantage, of course, is that then your instruments can be bigger because you don't have to get them all the way out the gravitational well. So you've got that combination of really good instrumentation that you get on the ground, but as high as possible above the atmosphere. And it's especially good at mid-infrared, where there's a huge cutout. You can't really see anything through the Earth's atmosphere. That's one of the reasons why James Webb's going to be so phenomenal in changing our understanding, because it's got these mid-infrared instruments that can view wavelengths you just can't see from Earth. And we wanted to look at ionized water, specifically at Saturn, I think, because of the in-streaming material from the rings into the ionosphere. We thought we would be able to see banding from that and the processes of the ionosphere. And we wrote, our colleagues of ours wrote an amazing proposal, got accepted. We were all gearing up to get to fly on a plane with a telescope, which would have been amazing. And then they cancelled the program. It's very unfortunate.
are there any balloon-based infrared telescopes?
Not that I'm aware of, no. I suppose one of the issues there is there's a big balloon above you.
So yeah. Yes.
But theoretically, you could do it, I guess, sideways viewing. But it's very difficult. I mean, coming up with ways to get past the atmosphere of the Earth is really tricky. The reason that Maunakea is so amazing is partly because of the conditions, but also partly because it's in America. It's got really good connections. You can drive to the summit in an hour. It's got electricity, it's got power. It's really well linked in. You've got really high speed internet. The best and it's also near the equator. That's the other thing that makes it really good. So you can see nearly all of the night sky from Hawaii. There's just a bit of the southern pole you can't see. The best observing in the world, as far as I've heard, is technically the southern pole. There's sites in the southern pole where the seeing is almost an order of magnitude better than Maunakea at times, but you're in the southern pole. So there is a telescope there now. They have built a telescope there that is able to do certain science, but you can only see the southern pole, so you can't see any of the planets from there because they're basically down on the horizon the whole time. So it would be absolutely useful for what we do, and it's dome sea in the Antarctica. People can't even survive there over the winter. It's so harsh. So I mean, it's literally almost the worst place in the world to build a telescope. But the conditions are amazing. So there's always this trade-off, right? And that's how you end up with a $10 billion space mission that produces data that is unfathomably good compared to what you can do from Earth, because it's so much better. But the reality of that is that it's oversubscribed 10 to 1. There's no way you can do the science you want with it unless you build 10 of them, and no one's expecting 10 to be built, right? And that's just for this wavelength window. There's all the other wavelength windows that are interesting as well. And so there's still more demand for this 3-meter telescope than can be met. And it's, must be the 20th or 30th largest telescope on the planet. It's because it's able to be used so prolifically for planetary science that makes one of the reasons why it's good. But really the reason is the instruments that it has. These instruments that we're using to split the light up are some of the best instruments in the world. And so even if the telescope itself is smaller, the people working on it are the best people in the world, and they're producing these insane data products that we can use and point at different planets and get amazing results from. And there's a huge wealth of astronomy, all different wavelengths, all different instrumentations. I sometimes hear people say, now we've got James Webb, we don't need anything else. Why, especially with Starlink, people argue vociferously that Starlink isn't going to ruin any astronomy because we've got James Webb, so we don't need anything on Earth. But, the amount of data that we're taking is huge. Even on this tiny telescope, the data products are world leading. We're writing papers that are going into some of the best journals in the world with this instrument, and it's oversubscribed. So imagine how much more oversubscribed VLT and Keck and all of the big telescopes are, let alone James Webb. So there's a lot of astronomy to do. There's a lot we don't understand about the universe.
And while we wait for the observations to come to an end, which I'm guessing are only a few minutes now.
We are finalizing up there. They quit out now because the time is 1:46, so the next astronomers are coming on now to do their program.
Excellent.
So,
Well, I was there's a couple more questions on YouTube. One is similar to Cinder issue, which is just about how much of the JWST viewing time will be used in our own solar system compared with deep field observations.
I think the current, so very specifically, we've been told that demand is matched by the proposal demand. So the more people that ask for time and the more time they ask for each individual subset of data, the more time they will be allocated. So it's very hard to balance these things, and that's one fair way to do it, right? The more people that ask for time, the more likely you are to get time. I think solar system is around 10% right now. I'm not sure. We probably benefit a little bit from observations taken outside of that program, because it's always nice to have a nice image of Jupiter or Neptune or Uranus. So a lot of those images that we've seen have come back as a result of no one in the scientific community taking those data. That's the core of James Webb going, well, this would be a good thing to do. Take a nice picture. But we're doing our best to make sure that we're proposing for as many interesting solar system objects as possible. One thing that we found in the last 2 rounds is that there's a lot of solar system science being done, but not very much planetary science. So I think that's sort of understandable, because the planets are big and bright, so it's quite easy to do a lot of the science that we want to do with ground-based. Whereas if you've got an asteroid that is incredibly small and dark, then it's much harder to do that science from Earth, and that sensitivity increase is really good. So there's been a lot of moon stuff, a lot of asteroid stuff, but very little in the way of planet observations. There's been a few observations as a part of the guarantee program, including Mars. There's some amazing, interesting observations of Mars recently announced. I mean, I know, but as much as anyone else looking on the internet about that, but we're going to keep proposing. But I mean, it's very unusual that you get time to do these planetary observations. So we're really, I mean, I can't overstate how surprised we were and pleased we were to get this time. It wasn't a surprise that we got the time. It was a shock. We were stunned for days after the announcement. We really didn't expect to get time. There's so many incredibly powerful proposals that are exploring all sorts of different science surrounding the planet. So it was really amazing for us to get that time.
Excellent. I've got one other question. I know we're coming to an end now, so we should probably wrap this up fairly soon. But it was someone asking about the use of occultations of stars and whether those are used to observe Jupiter's atmosphere.
That's certainly true. So the occultation that happened with Juno was specifically of the radio signal, and those have been used more. But it is possible to use stellar occultations. They explore a different sort of science. Generally, they're looking at the neutral atmosphere, not the electrons. So it's for the ionosphere, it's very much the radio signal that's the strongest, but it is associated because you're still looking at that top layer of the atmosphere mostly. It is interestingly something you can only really do some years because you need stars that are bright enough to do it. And so you're typically waiting for Jupiter to go into the Milky Way galactic plane, because there's so many small stars in the galactic plane and away from it. So it's certain times of the Jovian year that you can do it, because Jupiter's moving around every decade, and we have to wait till it moves to the bit of sky that the Milky Way is densest in order to get enough stars that there's a chance that we'll see. And I think that will be coming up. There's the possibility of that. And it's been discussed for other planets too. So there are observations where we've done it. You can also do it with the sun if you're on a spacecraft. So that's another way you can do occultations. And certainly there was UV occultations with Cassini, for instance, which are incredibly important for our science because they're telling us the temperature at the very top of the neutral atmosphere. So that's a really good counterpart to our measurements. So it is fundamentally important science for us. But if you can imagine how hard it is to do with the sun from Saturn, doing it with any other star than the sun, even if you're much further away from the sun than we are at Saturn, it's a hard thing to do. It used to be used a lot more. I think it's not so common these days, but it's something that we potentially return to with adaptive optics and things like that. I think there's more call for it now.
Okay, thank you. I think I can't see any further questions in the chat, so I suggest we wind this up if that's okay with everybody. Yep, one thank you note in the chat on YouTube, so I guess that's a good sign. I just want to thank you all for spending the time to do this today and sharing this with us. I know you were going to be observing anyway, but I do appreciate the additional stress of trying to juggle the two things at once. So thank you to Henrik and Paula and Tom for giving me time and sharing this with the wider public. For anybody who is watching, the RAS does put up various things on our YouTube channel from time to time. Most notably and frequently, we put all of our public lectures up as well, and they're completely free to view. We also have things like our ordinary meetings, our monthly scientific meetings. If you want to have a deeper dive into things, those are available as well. And that's all, entirely free content and shareable, and we encourage people to do that. So I can actually even see one final question, which is asking about proposals for another Jupiter probe. I'm sure the answer is yes to that, because astronomers are always proposing new probes, right? So but does anybody want one final word on what probe's coming next for Jupiter? I mean, we've got the JWST mission on the way, obviously, but
yeah, so there's lots of missions talked about and lots of missions coming. JWST is going to arrive, and the Europa Clipper from NASA as well. So there's an ESA mission and a NASA mission, and other missions to Jupiter. None of them have a probe that goes into the planet. I think that's unlikely for Jupiter again. There is discussions about whether that could happen for Uranus. We're definitely aiming to go to Uranus next. It's the next big target for a large-scale mission, because NASA has prioritized that, and there are discussions about whether there should be some form of probe. I think it would be incredibly beneficial. As science you can only do with a probe, but it's a hell of an undertaking. So how that would work and whether that would work is under debate as we speak. People,
how long does it take a mission to get to
it's a bit depressing. That's how long it takes. So the problem with the problem with Uranus and Neptune is that it's really hard to get to, and you can get there a lot quicker if you stop by Jupiter on the way. You can get a gravitational assist from Jupiter, but then you have to wait for Jupiter to be lined up correctly. So there is an opportunity coming up for that in the, I think, the early 30s, so about 10 years, which is quite tight for a whole mission to be put together and built and launched in that time frame. But that would get us there by about 2040, I think. But it's unlikely that will happen on the time frame we're talking about, at which point you slide about 10 years down the road. So suddenly we're talking 2050. at which point I will be well into my retirement age, even with nominal slippages of how late we're allowed to retire. It's likely I will be retired by that point, which is a little depressing. The more depressing thing is that Powell will probably be nearing retirement as well. Even though our youngest scientists are, going to be the most austere of grandiose people at the back of the room at that point. So these missions are very much kind of multi-generational plans, and that's why talking to schools is really important, because it's very possible that the person in the school at the age of 15 will be the person in the stage of career that I'm at now when we get to Uranus or Neptune. So that's
something to aspire to, yeah. And when I'm looking at Paolo, thinking, yep, she'll be probably not quite retired by the time it gets to Uranus. So potentially a whole scientific career based on a mission like that, getting there and analyzing it. But anyway, with that, I think I'll leave everybody to it. But thank you for joining us, and thank you to everybody for watching. And we'll hopefully see